Welcome to the CMU SEI Research Review 2020.
Hey, welcome to the day 2 of the 2020 CMU SEI Research Review. Boy, we're sure glad you're back. I'm Tom Longstaff. I'm the Chief Technology Officer at the Software Engineering Institute. The SEI is a federally funded research and development center at Carnegie Mellon University focused on software engineering, cyber, and AI engineering. Yesterday, if you were here, you heard from a lot of our researchers on the AI engineering portion. Today's objective is attaining autonomous cyber operations and resilience, enhancing operational resilience, equipping the cyber and information operators with dominant tradecraft, and preparing the cyber and information operator for mission. The way our fundamental research works is we are always looking to get this kind of research moved into the creation of tools and techniques which can eventually transition directly into DoD and other government agencies to really enhance mission and make this happen. So our work really does represent that transition from, basically the fundamental research you're going to see all the way down to where we're going to prepare this for the future. Today's Master of Ceremonies is Roman Danelu. Roman is going to frame the day right after I'm done here. Speaking of that, feedback is really encouraged. I know that a lot of you have been to many cyber conferences and many of these virtual events that are out there. I'd really like to know what works, what we've done well, and where you've seen it done better in other places. We will probably keep some elements of this kind of remote event going into the future, even after COVID-19 is done. And we are really excited about maybe integrating some of this into future research reviews. So I really hope you enjoy hearing about CMU SEI's fiscal 2020 research efforts, and that you see in the presentations the pride that we take in our work and connections to what might help you prepare your mission in the future. I'll see you at the end of the day for the 2020 wrap-up. Now over to Roman Danelu for the framing for day 2. Thanks.
Hi, Thank you for joining us. My name is Roman Danilio. I'm the Deputy Chief Technology Officer at the Software Engineering Institute. It's my pleasure to welcome you to our second day here of our annual research review. Yesterday was primarily focused on algorithmic advantage and looking at and talking about areas like AI engineering. Today's focus is going to be on SEI's work in cyber. This is a very broad area of activity and also a warfighting kind of domain. So before we get started, I wanted to focus you on the three research questions that drive what the SEI is doing. The first is how to increase the trustworthiness and confidence in all phases of the systems engineering lifecycle. This body of work covers things like how do we improve how this engineering is done? So these are approaches to design and testing. It's also recommendations on what architectures work for which sets of kind of problems and can get as specific as code should be written in the following way. We call this designed-in resilience. The next research question for us is how to conduct mission-focused defense. This is about how do we appropriately measure system posture and how do we field appropriate defensive mitigation actions that ensure that there's a higher likelihood of mission success. This is a process where you take technical posture measurements of individual systems and you synthesize them into an all hazards calculus that informs the commander on the way ahead. This is strongly informed by taking a look at external threat, taking a look at adversary capabilities, also looking at insider threat, but it also considers risk through the supply chain and other dependencies that may occur through critical infrastructure. There's also a significant economic component to this body of work because there is not infinite resources to necessarily roll out necessary security kind of protections. We call this operational resilience. The third of the research questions is focused around how to ensure that operators have the effective tradecraft that they need to do cyber operations. The biggest component of that is how do we move humans out of the loop? How do we leverage autonomy to help us get the scale, the speed, and the persistence in planning, identification, response, and recovery activities, while at the same time injecting the human expertise where it's needed? A big component of that is figuring out the human-machine teaming elements of those new autonomous cyber tradecraft elements, but also how do we pivot the workforce to do that class of mission with these new kind of tactics, and how do we ensure we get that necessary capacity? That's a lot of work in the SEI kind of portfolio. What you're going to hear about today, and first after the break, is going to be a few talks and panels focused on different aspects of this designed-in resilience. We know that addressing defects, the cost of addressing those defects rises about an order of magnitude through every phase of acquisition. So things you find very early during design time are relatively inexpensive to fix, relative to security issues that may be found after the system is fielded, tend to be much more expensive. So the question is, how do we do the necessary resilience engineering at all phases of that life cycle? The SEI has two big pushes in that area. First, it's around digital engineering, which uses formal models to define system properties, and you use that primarily to identify architectural vulnerabilities and poor requirements that have security implications, and you can do all of that before the code is even written. A lot of the work, in addition to developing those digital engineering strategies, also around adoption. There's a learning curve there, and at times it can be steep. So what does it take to get that into programs? There's also about how do you harmonize that digital engineering with the other engineering activities that are happening. Specifically, how do you do digital twin, which is a topic you'll hear more about tomorrow, where you reconcile the software models with the physics models of complicated cyber physical systems. Likewise, how do you integrate this model-based engineering with the activities in continuous integration and continuous deployment? So with DevOps. And this DevOps and imbuing security into the CI/CD pipeline, which colloquially is referred to as DevSecOps, is another big push for the SEI. Automated code inspection is a proven approach to hammer out and remove potentially problematic areas of code. But the challenges are you got to make sure that those specific automated approaches both scale to the code bases that you need and scale both to the code base and also the various processes that are required to handle the output of that code analysis. And it's also a matter of making sure that there's automated test regimes for all the different technology that you want to build systems around. You heard quite a lot about the big challenge yesterday when we were talking about AI engineering and the challenges of doing test and evaluation and how those regimes need to change. The key consideration as you insert more of this automated testing is to ensure that the rapid velocity that you initially got by making an investment in a CI/CD pipeline can still continue. With digital engineering and DevSecOps, the eye is towards first doing things as early in the life cycle as possible, but also two key tenets. It's the idea that we want to find system vulnerabilities, not just those in point components. And secondly, it's about producing evidence that can inform the continuous authority to operate processes to ensure that the security testing is not a barrier ultimately to fielding new capabilities. Now, where the design resilience meets cyber operations, another kind of area of work for us, is that the systems themselves need to be engineered to support their own defense. No matter kind of how effective the design and practices are going to be, operational circumstances or adversary action is going to result in mission jeopardy through the compromise of those systems. So there's design principles and architectural principles that need to also be baked in that the SEI is working on. So this is about ensuring that these tools can be fielded on flexible infrastructures that allow dynamic posture changes. It's reducing the coupling between components to reduce lateral movement of adversaries. So this idea, we want to reduce the trust between those components. And we also need to make sure that the cyber teams have sufficient visibility into the operational state of the system to direct mitigation actions. And the big research area is honestly to also combine those approaches together to ensure that the ops in the field ultimately informs the future design of systems. The first thing you're going to hear this morning is actually going to be talking about some of that operational tradecraft. And later in the day, you're going to be hearing about research into the readiness of the operators. The central tenet of the first talk is going to be about how do we help the human analyst by bringing AI to the cyber mission? How do we reduce the time in this particular case to do that analysis from things that would take on the order of hours to doing it on the order of seconds? In the afternoon, the flavor is going to change a little bit, where this is going to be focused on how do we get additional agility for the human operators, given that they are moving from being in the loop with their new cyber tactics to being on the loop and managing the autonomy there. It's an exciting area to, of course, be in. And like you, I'm sure you want to hear a lot more about some of the talks that are going to be coming. So with that, I'd like to get the day really started for us and turn things over to Mr. Jeff Gennari, who's going to be chairing our first panel around doing binary code analysis, an element of our cyber operations work. So over to you, Jeff. Thanks.
Welcome. My name is Corey Cohen, and I'm the leader of the Executable Code Analysis team in the Threat Analysis Directorate at the CERT Coordination Center at the Software Engineering Institute. Today I'm going to be presenting with my colleague, Dr. Edward Schwartz, about advancing cyber operator tradecraft through automated static binary analysis. This presentation has been cleared for public release. On the Executable Code Analysis team, we've been building tools to solve DoD program analysis challenges for a while now. Historically, our work is focused on malware reverse engineering, but more recently we've also been focused on software assurance and vulnerability discovery. We maintain a platform that we call the Facets Static Binary Analysis Platform. In this platform, we build a wide variety of tools that are focused on making a difference for operational DoD cyber tradecraft needs. The Facets Static Binary Analysis Framework includes a whole bunch of features that are useful for building static binary analysis tools. and a number of them are listed in the blue box, and I'm not going to go into the details of those, but suffice it to say that they're useful for building tools like the ones we're talking about. The Faro Static Binary Analysis platform is built on top of ROSE, which is maintained by Lawrence Livermore National Labs, and we have a very close partnership with them. Their ROSE compiler framework is highly extensible, BSD licensed, and implemented as a C++ library. As a consequence, our Pharos framework has many of those same properties. Our Pharos framework is available on GitHub at the URL listed on the screen and on the board behind me. We've built a wide variety of tools in the Pharos framework. Today, the only one on this list that we're going to be talking about is OO Analyzer, but I wanted to give you an idea of the other kinds of tools that we've built in the framework, so that if you visit our GitHub website, you can look for things that might be interesting or relevant to your operational needs. For today's agenda, we're going to discuss 3 examples of how the executable code analysis team has been advancing cyber operator Tradecraft through automated static binary analysis. The first topic is program reachability for vulnerability and malware analysis. This is an early research topic where we're trying to bring the very best academic research to bear on new problems in operational use. The second topic that we're going to talk about is recovering meaningful variable names in decomiled code. This is an instance where the team has built a prototype tool. We've been testing it, and it's basically ready for transition, but we haven't actually transitioned it quite yet. In the third section, we're going to be talking about object-oriented construct recovery using our tool OO Analyzer. This tool has been fully transitioned. It's been in use by operational DoD operators for a while, but we've been making improvements and maintaining it to better meet the DoD's needs. In this portion of the presentation, we're going to be talking about an early research topic that the team has been investigating: program reachability for vulnerability and malware analysis. The problem that we're facing here is that highly skilled Department of Defense malware and vulnerability analysts currently spend significant amounts of time manually coercing specific portions of their executable code to run. Basically what we're saying here is that they have a vulnerability or a piece of malicious code that they'd like to see execute. They don't know how to get it to execute. And so they have to figure out how to execute it before they can begin analyzing it. Our solution to this problem is to automate the analysis of the binary code, choosing program inputs that trigger specific behavior, and then to reduce the time that the cyber personnel spend performing these complex software analysis tasks about under what conditions the code is reachable. Our approach is to use techniques from the software model chalking community to identify these inputs and to generate a simplified executable that's free of all these complex and convoluted dependencies, so that the analyst can put it in a runtime environment, and when they run it, it'll just execute right to the parts of the program that they're interested in observing. This diagram shows the architecture of our proposed pathfinding tool. On the left-hand side is an assembly language listing that has some code that's of interest to the analyst. It might be malware, or it might be a vulnerability that they're interested in demonstrating. And the analyst wants to know, under what conditions does this malicious code or this vulnerability execute? So our approach here is to take this assembly listing and lift it into an intermediate representation, and then express that intermediate representation as what's known as a Z3 SMT constraint problem. SMT stands for Satisfiable Modulo Theory, and it's an area that's been getting a lot of research and program analysis over the last several years. Basically, it takes an algebra problem, a Boolean algebra problem, and says, is this satisfiable given all these constraints? Which we can think of as, is this code reachable under a given set of input constraints? And the SMT solver will come back and either say, no, this is not satisfiable, or yes, it is satisfiable, and it's satisfiable under the following conditions. For example, when the ECX register is 42 hex, and when the check system call returns 34 hex, then the point in the program that you were interested in reaching executes. We can use that information to perform the transformation of our executable code to produce something that will run directly to the interesting parts when executed. In this research, what the team has been doing is it's been evaluating multiple different approaches and implementations to generating that IR and proposing or constructing the SMT constraint problem. We've looked at 4 different approaches: the Pharos function summary approach, the weakest precondition approach, the property-directed reachability approach, and a Ghidra-Seahorn-based approach that also uses PDR. We've been evaluating each of these approaches for accuracy and scalability to try and understand which one best meets the needs of the cybersecurity operator analyst from the DoD. So the first approach that we've been looking at is the Pharos function summaries approach. This is the one that's been historically used by the Pharos static binary analysis platform in tools like OO Analyzer, which we'll talk about a little later today. This approach is an approach that's designed to be simple. Memory is represented very simply and very efficiently as a scalar map that maps an address to a value. And while this is very easy to implement and works for some circumstances, it's not actually a very rigorous or robust way to represent memory. Loops are unrolled, and that means that there are some paths that we're not able to reason about correctly and that we're not able to prove are in fact reachable. Overall, this approach has proven to be great when it works, but we knew it had some limitations, and as we've been working through this research, we've gotten very effective at demonstrating exactly what those weaknesses are and how it doesn't really meet the needs of analysts in this particular problem domain. The second approach that we've been looking at is the weakest precondition approach, and this approach uses the Pharos static binary analysis framework to produce an intermediate representation. And this intermediate representation is much more accurate because it uses the full semantics of the instructions to model the program much more accurately than the Pharos function summary approach did. We've also represented memory more precisely using a single large array for the entire stack. And this has some performance problems. It's not the most efficient way to represent the memory, but it is much more accurate. And unfortunately, those performance problems could be an issue, but we've got some good news there, which is that the weakest precondition algorithm is known to generate formulas that are linear in size for the SMT solver. So there are some, it's kind of a medium balance here. Overall, we expect or know that this weakest precondition approach will be more accurate than the Pharos function summary approach, but the real research question going into this research was, can it be made, can the PDR approach do better? So this property-directed reachability approach, or PDR approach, it comes out of the software source code model checking community. And it's able to reason much better about loops, and we'll talk about that more in a moment. But the problem with the PDR approach is that it hasn't really been used on binary executables. It's a source code approach. And so to address these issues, we formed a collaboration with Dr. Ari Gerfinkel at the University of Waterloo. He's a world-renowned expert in Z3 and SMT and PDR, and in fact, he's the creator and maintainer of the Spacer PDR engine, which is the PDR engine that ships with the Z3 SMT solver by default. And throughout this research, we've been working with Ari to improve the support for bit vectors and arrays and the portions of program reasoning that we knew were going to be problems in the binary domain in comparison to the source code domain. So this PDR approach, how does it deal with loops better? Well, it's able to reason about loops in such a way that it can make observations that the other two approaches cannot. So for example, it's able to conclude that a particular loop will never terminate, and therefore the code after the loop will never execute. It's also able to reason iteratively and inductively over loops to figure out things like, this loop may go around some some indeterminate number of times, but it always exits when x is equal to 3. Or it might be able to conclude that y is equal to 4, and because it's not modified in the body of the loop, y is also equal to 4 at the end of the loop. And these advancements in loop reasoning mean that we're able to reason about paths and their reachability much more accurately in the PDR approach than we are in these other approaches. We've used the same memory model and the same IR that we used in the weakest precondition approach, so we're very comparable there. But what's different about this PDR approach is that it's shown a lot of performance problems. It was designed for the source code domain, where the functions are all broken up into individual stack frames. And so this memory model where we represented the entire stack as a single memory array created a lot of problems, and it struggled quite a lot with performance. We've also noticed that the PDR engine occasionally gets stuck trying to guess the individual bits of a large register, like a 64-bit register. So overall, this approach is very accurate, but has some performance problems. This led to the proposal from Dr. Ari Gerfinkel that we try another approach, a Ghidra and a Seahorn-based approach that also uses PDR. The observation that we made here was that the Seahorn tool, which is the source code analysis version of the Spacer PDR engine, it was doing very well on the test cases that the PDR engine, our previous approach, was struggling with. So we had this idea that maybe if we could lift the problem to the same level of fidelity that the source code tool was already working on, that we would have a solution to our problems. So the idea was that we would use the Ghidra decompiler to produce something source code-like and lift that into LLVM and then invoke the Seahorn source code analysis tool in order to get an answer for the reachability question. This approach has the same strengths as the previous PDR approach in terms of its loop reasoning, but instead of modeling the entire memory of the stack as a single big array, we're now breaking each function up into its own little memory array, which is accurate within the function, but saves the SMT solver from having to struggle through some of the interprocedural concerns. This approach is promising, but our big question here is how accurate is the decompilation, and how well can we really lift into LLVM and represent this source code version of the problem? So this slide summarizes our results, and I don't want you to dwell on the numbers. I just really want you to look at the colors. We've color-coded them such that red is the worst result for all of the approaches. Green is the best result for all of the approaches. And then there's two colors that are yellow, kind of a light yellow that represents the second place result, and a golden color that represents the third place result. We took 91 source code examples, and we compiled them at two different architectures, 32-bit and 64-bit x86, and on three different compilation levels, 00, 01, and 02, which we've labeled here as none, medium, and high optimizations. In total, this was like thousands of test cases. And I think the colors really help you see the trends here. They're largely what I've already talked about. The Ferris function summary had the most failures and the fewest passing tests, which means it really, frankly, did kind of badly. But it also came in first on the number of timeouts, having the fewest timeouts of any of the approaches. So this reinforces our idea that it's the least accurate and yet the highest performing approach. The weakest precondition approach is actually the one to beat. This is the one from the academic literature that we started with, and it's still doing the best. It had the greatest number of passing tests and came in second on both failures and timeouts, so it's doing okay there. But we know that this approach has known deficiencies, which is why we wanted to bring a more sophisticated approach like PDR to bear on the problem. So how did the PDR approach fare? Well, pretty much as we expected. It had the lowest number of failures, meaning that it was the most accurate, and when it produced an answer, it was the most correct. But the number of timeouts was the worst timeouts of all of the approaches that we looked at. And this was caused by those problems in memory modeling and bit vectors and so on. The Ghidra-Seahorn approach came out in kind of a disappointing third place. The good news here is that wasn't because of the path reachability problems that were causing the other approaches to have difficulty. The problems here were all in terms of our ability to accurately lift the binary into a source code representation and transform it into LLVM. So this means that longer term, if we can improve those pieces, this may turn out to be the best approach, actually. I think it's pretty clear here that there's no clear winner. They all have strengths and weaknesses. And despite, a couple of years of research here, we've not been able to make any one of these perform substantially better than the others. So in summary, path reachability and binary executables in particular continues to be a very hard problem. We've got all these approaches. There's the Ferris function summary approach, and it's not accurate enough. There's the weakest precondition approach that's technically the winner and does pretty well, but it has known deficiencies that prevent it from accomplishing our original goals. We've got this spacer approach, PDR approach, that is very accurate, but hasn't quite met our performance needs to be applicable. And we've got a Ghidra-Seahorn approach that's promising, but is stuck on other fundamental research challenges in raising the accuracy of the decompilation. The good news here is that we've got an excellent test suite. We're able to evaluate these very clearly now and very easily, and our team intends to continue to monitor each of these approaches in order to see which one eventually pulls out to become the clear winner in this race, so that we can solve this problem for the DoD at the appropriate time. We may also conduct some additional research into completely different approaches, like dynamic approaches involving concolic execution. At this point, I'm going to turn the presentation over to my colleague, Dr. Edward Schwartz, to talk about a piece of work on the team that's much closer to operational transition, some work we've been doing in variable name recovery during decompilation.
All right, thanks, Corey. So I'm now going to talk about a different project at the SEI that's a little bit farther along in the research pipeline, specifically how we're working to automatically recover meaningful variable names in decompiled code. So I want to start off by talking a little bit about the different types of tools that a reverse engineer has at their disposal. So what you can see here is an example of a very basic disassembler, which essentially takes the bytes in the executable and represents them in the form of assembly instructions. Now, there are also more sophisticated disassemblers that make things quite a bit easier to analyze. They can be interactive, and they can have graphical interfaces that show you the control flow and the data flow in the program. And all of these things make it easier to analyze the program. But at the end of the day, the reverse engineer is still reading assembly code, which is not always easy, even for people that are very familiar with it. So a more recent trend has been the use of decompilers in reverse engineering. So a decompiler tries to reverse the compilation process. So as an input, it actually takes an executable, and as an output, it produces high-level source code, usually in a language such as C. So this is a screenshot of a very popular decompiler that's called Hexraise. And if we zoom in here, we can take a look at the type of output that it produces. And it doesn't look like assembly code, and it certainly does look a lot more like C. But the longer that we look at this, we can kind of see that there's some aspects of it that are not normal for source code either. So it doesn't look quite like normal source code we're used to reading. And there's a couple of reasons for this, but the one that I want to talk about today is that decompilers typically don't do much work to try to assign good names to variables. And let's look at an example here. So here's some decompiler output, and we can see that the variables are named v1, v2, and v3. So they're not really giving us any information about how those variables are being used. So the goal of our work is actually to take decompiler output like this and refactor it to add meaningful names to the variables. So for instance, we might call v1 fd, short for file descriptor. We might call v2 size, because it's used to indicate the size of a memory region. And we might call v3 ret, because it's used to temporarily store a return value. So that's the idea behind our work, is to actually give these variables names that will help the analyst understand what the variable is actually being used for. So I want to start off by talking about some good news, and that's we are able to actually recover up to 74% of the original variable names in a large corpus of code and executables that we gathered from GitHub. And we're really excited about that result. I want to talk a little bit about why that's actually possible for us to recover variable names in the first place, though. If you've ever worked in binary analysis, or if you just have a good understanding of how compilation works, you might have heard this common refrain that there's information, including variable names, that is simply lost during the compilation process. And there is truth to this. The variable names aren't stored by the compiler in the executable. So it's not something that we can simply, recover in a very easy fashion. So what we try to do instead is we actually try to predict a variable name in a statistical fashion by looking at lots of examples and looking at the context in which the variables are used. And some of the ideas for this type of learning come from a concept that's called natural language. So we know that natural languages like English can be really complex. So, we have poetry and we have really elegant prose. But the idea behind natural language is that actually most utterances, most of the things that we say or write, are very short and repetitive. And there's obviously some evolutionary reasons for this, right? If there's a predator or some other danger, we're not going to stop and write a poem about it. We're going to try to convey the sense of that danger in as few words and as quickly as is possible. Now, what does this have to do with decompilation? Well, a few years ago, researchers proposed a theory that software is actually natural as well. And in a similar vein, there are very elegant algorithms and implementations and designs, but there's also a lot of source code that is extremely repetitive. So the graph that you can see on your screen here is actually showing you the results from a study of repetition in a Java corpus of software. And the point that's highlighted on this graph is actually showing you that 70% of the sequences that are longer than 20 code tokens actually were written somewhere else inside of the corpus. And so the bottom line is that programmers are writing a lot of code that someone else has already written. And that's something that we can actually use to our advantage when we're trying to predict or learn variable names. So how does that work? What's the big idea? Well, we're going to learn what a typical or reasonable variable name is for a given context of code by looking at lots and lots of examples. And the idea for why this works is that if software is repetitive, then names must be repetitive as well. And I'm going to demonstrate this to you with a simple example. So here's a snippet of code, int main int, and then blank. And I want you to think to yourself, what code is likely to go under the blank? If I were to tell you that banana goes under the blank, I'm willing to bet that most of you will say, no, that doesn't seem quite right to me. But if on the other hand, I were to tell you that under the blank is argc, you'd say, oh yeah, I've seen that many, many times. That must be right. And so that's what we mean when we talk about trying to predict a variable name based on the context of the code in which that variable is used. So to learn how to name variables in this way, we need to have a lot of examples. And the good news is we can actually generate examples automatically. We need to start with code. So what we did is we scraped GitHub and we got lots and lots of source code. We then tried to compile as much of it automatically as we could, and then we took the resulting executables and we decompiled it using a decompiler. So at the end of the day, we wound up with this very large corpus where on one side of the corpus we have original source code with meaningful names that the programmer assigned. And on the other side of the corpus, we have the decompiler output with the placeholder names like v1, v2, and v3. So how many examples were we actually able to create in this way? Well, we created over 160,000 unique executables, which is a lot. And in those executables, when we decompiled them, we wound up with over 1 million decompiled functions. So quite a bit of examples. And then we split this information that we had by executable into testing, training, and validation sets, which we then used to try to automatically learn how to do this naming. So how do we actually learn how to name variables from all these examples? Well, we use them to train a neural network. I'm not going to go into a lot of detail here because, to be frank, my colleagues are really the experts on this. But at a high level, we use a technique called a sequence-to-sequence model, which consists of both an encoder and a decoder. Our model is a little bit unique in that it has two different encoders. We have a lexical encoder, which you can think of as essentially encoding the source code representation. And we also have an encoder that's structural, that takes information from the abstract syntax tree and encodes it into the neural network. And what we found is that we actually needed to have both of these encoders to be able to recover as many names as possible, which was a little bit surprising. We actually thought that the structural encoder would outperform the other one. So that's a little bit about how we actually do the learning, but what everyone wants to know is how well are we actually able to recover these names? And answering that question is actually a little bit difficult because what I think of as a good variable name and what you think of as a good variable name might not be the same thing. And so to avoid that whole subjectivity problem, we made an assumption that most of the time programmers give a variable a name, they think about it and they try to give it a good name. So we're just going to assume that names in the original source code are good. And that allows us to simply count how many times can we actually recover the original name from the decompiled code and use that as a metric to see how well we're actually recovering meaningful names. So I already spilled the beans on this a little bit. And remember that we're able to recover around 74% of variable names exactly. But one caveat is that we have a lot of data and we need to use all of that data to be able to get that level of accuracy. What this graph is showing you is that if you don't use all of the data or all the examples that we have, our accuracy drops quite a bit. The other takeaway when it comes to our evaluation has to do with code similarity, specifically how similar code is that we've trained on to the code that we're looking at. So in some cases in reverse engineering, you might be seeing new code that you've never seen before. But in a lot of cases, you've actually maybe seen that code before. This could be because of natural repetition, like we talked about. It could be because libraries get linked in to the executable, or it could be because code is copied from one project to another. So we observed this in our corpus because we saw functions, the same functions occurring in multiple executables. And so because of the way that we split our training and testing sets, sometimes that means that a function could occur in both the training set and the testing set. And that's something that obviously affects our overall accuracy. And that's what this graph is trying to show you. So if we have a function that is in both the training and testing sets, for instance, because it's a function that appears in a library, then we're able to actually recover names about 86% of the time. So we do a little bit better as you'd expect. If we look only at the results for functions that we didn't train on, then we drop down a little bit to 35%. This tells us two different things. One is that repetition and similarity are of course very beneficial and make it easier to learn how to predict a variable name. And two, there's a lot of repetition on GitHub, which we can see because our overall results are actually much closer to the 86% line than the 35% line. The other thing I want to mention is that not recovering the original variable name is not necessarily a bad thing, right? We can still recover variable names that are meaningful even if they're not the original. And I want to show you an example of that. So here's just another snippet of some decompiled source code. And the original names that the developer assigned to these different variables were file name, mode, and is private. So if we look at the names that our system was able to recover, we actually recovered file name and mode exactly correctly. But the third variable we actually named create instead of is_private. So that might seem bad, but if you actually look at this code and see what it's doing, when that last flag is set, it actually creates a file with private permissions to make sure that different people can't read the file. And so, we're not naming the variable the exact same thing, but we're still giving it a name that reflects the way that it's used. And that makes it easier to understand and read the function, which is our ultimate goal. So one of the themes about our talk today has been about how we can take cutting-edge research and transition it to practice. And last year, we actually talked about this project when it was really cutting-edge research. And at the time, we had this proof of concept that really wasn't usable in practice, right? It was useful for us to demonstrate that this was theoretically possible, but a reverse engineer couldn't use it to actually look at code. So we've actually taken this and we've now implemented it as a hexphrase plugin for the hexphrase decompiler that makes it really, really easy to use this system to predict variable names. So here's a screenshot of hexphrase with the plugin being used, and it's a little bit hard to see, but all that the analyst has to do to actually trigger the system is press the P button on their keyboard to predict new variable names, and then everything else happens automatically behind the scenes. And I want to show you another example of what some typical results from the system can look like. We're clearly not getting the original variable names, but this is a good example of how we're still getting meaningful variable names. So we have names like the M for the environment, the return, the model, the width, and so on. These aren't exactly the original names, but they're still conveying information about how those variables are actually used in that code. And so they make it a lot easier to read. So in conclusion, software is highly structured and predictable. And we can actually use that to recover meaningful variable names by studying and learning on a lot of existing source code. We were able to recover up to 74% of variable names in our GitHub corpus, and the uniqueness and the similarity of the data is actually very important for predicting how well our system will work in practice. So with that, I'm going to turn things back over to Corey, who's going to talk about a different project, which has to do with recovering object-oriented information from executables.
Thank you, Ed. In this portion of the presentation, we're going to be talking about a tool that's actually reached operational relevance amongst reverse engineering analysts. Specifically, our tool called OO Analyzer that's used for recovering object-oriented constructs from binary programs, and the improvements that we've been making recently to that tool in order to make it more relevant to the DoD. So what's the problem that we're tackling with this tool? Basically, that object-oriented programs are very complicated, and they have these abstractions that are time-consuming and expensive to reverse engineer. It requires very specialized skills that are in high demand in the DoD. Our approach to solving this problem is to combine a lightweight program analysis pass with our handwritten rules written in Prolog that express our knowledge as domain experts about how object-oriented compilers produce executables. In this way, we're able to fully recover the object-oriented constructs from an executable. So just to make sure that we're all on the same page here, when I talk about object-oriented abstractions, what are we talking about? Well, we're talking about the actual classes themselves, but we're also talking about the methods that are associated with those classes, the members that are associated with those classes and sizes and offsets, the relationships between the classes, such as inheritance relationships and composition relationships. Collectively, these are what I mean when I say object-oriented constructs. Our tool begins by recovering these from an input executable. We run our tool and it recovers these constructs, which are then provided to Ghidra and AIDE Pro for interactive use by the analyst to understand what has been recovered. Our tool is composed of two components. One is a C++ component that extracts the facts from an executable using our ferrostatic binary analysis framework. And the other is a Prolog component that has three phases. We engage in some forward reasoning, and then we make some educated guesses in a hypothetical reasoning step, and then we consistency check that representation of the program, and then we repeat this cycle. And I'll talk about each of those phases in some more detail. So a common question at this point is, why Prolog? Well, one of the problems that we face in this particular challenge is that there's multiple source code representations that can produce the same executable. This means that it's not possible to just reason forward and conclude what the right answers are about that program. We instead sometimes have to make educated guesses in that hypothetical reasoning component. And Prolog is very important to us because it allows us to backtrack when it turns out that one of those hypothetical reasoning guesses turned out to be incorrect, and we need to consider another alternative. We also really like Prolog because it allows us to express that expert domain knowledge that we've been talking about as rules in the Prolog language, which is a very natural and an expressive way to talk about that knowledge. So the first component in our tool is the Pharos fact exporter. As I've said before, it uses the Pharos framework, and it intentionally favors scalability and over accuracy. So we're using that lightweight memory model and path sensitivity that we talked about earlier in the pathfinding segment. We're not using any of the fancy constraint solving approaches, but this is sufficient because we've designed our Prolog component so that it's able to overcome any inaccuracies or weaknesses in this fact exporting phase. So what kinds of facts are we exporting from the Pharos fact exporter? Well, they're all very low-level facts. So for example, we're talking about how object pointers are passed between functions, and we're talking about which functions access which offsets in the objects, potentially representing member accesses. We're tracking things like which members were accessed before they were initialized, and what addresses might possibly be virtual function tables. At this stage of analysis, pretty much none of these facts have been proven to actually be object-oriented facts, and we'll do that in the prologue section. So this is an example of some of those early facts that are reached through forward reasoning in the prologue phase, built on top of those low-level facts. There are things like, yes, this function really is an object-oriented method, or this function is a constructor or a destructor, or maybe that there's class inheritance relationships or class composition relationships. These kinds of facts are the facts that reverse engineers are actually interested in order to understand the object-oriented structure of the program. So we've talked a lot about the expert domain rules that express what compilers do, but I wanted to try and provide a little more detail on that. In our paper, we've expressed these rules in the syntax you see here on the screen, and basically that says if precondition 1 and precondition 2 and precondition 3 and so on through some n preconditions, if they're all true, then that must mean that C is also true. And that would be an example of a forward reasoning rule. But we can also use this same syntax to talk about a hypothetical reasoning rule, where we interpret things very similarly, only now we say, if all of these preconditions are true, that makes C a good educated guess. And we're going to try that first, and then we're going to run our consistency checking phase where we evaluate whether or not there's any contradictions in our model. And if there's not, we'll accept C, but if there is, we'll try not C instead, and repeat the process and try consistency checking again. So here's an example of a forward reasoning rule. This one says that if a method is called on a base class object, then it cannot be defined on the derived class. This follows our normal thinking that base classes aren't allowed to call derived class methods. But you might be inclined to think that the right thing would be to say, well, then the method must be on the base class. Turns out that's not actually correct, because it might be on the base class or any of the base class's ancestors. Instead, you have to say simply that the method is not on the derived class, and then let a later rule sort out which base class it's on. So here's an example of a hypothetical reasoning rule that does exactly that. It says if a method is called on a derived class, but not a base class, let's first assume that the method is on the derived class. If this guess fails, then it'll guess in a later rule that perhaps the class is in fact on the base class. So at this point, I'm going to turn things back over to my colleague, Edward Schwartz, to talk about how we've been improving the performance of OO Analyzer to make it more relevant to DoD analysts. Thank you.
All right, thanks, Corey. So we published this work on OO Analyzer originally back in 2018. And at the time, it really was an advance in the state of the art when it comes to research. As Corey described, a lot of this has to do with the unique prologue-based design, but it's also unique in that it tried to recover information about all the classes and all the methods in the executable, which most existing work did not, and it was also much more accurate than existing work. So it really was an advance in the state of the art when it comes to research. But one of our concerns was that, because we wrote this in kind of a non-traditional language of Prolog, is it actually the state of the art in practice as well? Can it actually scale to the executables that we need it to be able to analyze? And to answer this question, we graphed some of the experiments we did in our original paper, and the x-axis here shows how many methods are in each program compared to the y-axis that shows you how long it took to actually do the analysis. And if we look at this, at first glance, it looks like we have a nice linear relationship indicating that it scales fairly well. But as soon as we start to zoom out and we look at some larger programs, we start to see that this relationship starts to degrade. Now, to give you some context, right around here, around 1,500 methods is an executable called MySQL.exe, which is the MySQL client of the database system. And if we zoom out a little bit more and look at some even larger programs, MySQL-D, or the MySQL daemon for the server side of the MySQL system, has around 50,000 methods. So it's quite a lot larger. And if you look at this graph and the trend line that we see, it's easy to see that MySQL-D is going to take a really, really long time to run if it works at all. And that's very problematic because, DoD needs to be able to analyze these really large and complex pieces of software and to be able to do so in a meaningful amount of time so that we can take action on it. So what actually happens if we try to run OOAnalyzer on MySQLD? We ran it for about 18 days, and this graph is showing you the progress that it made over time, and the results were really disappointing. In the last 10 days, it made no progress at all. And this was really disappointing. Even though we were proud of the research that we did, OOAnalyzer was honestly too slow to be used on a lot of the programs where we really needed it the most, right? The most complex and the most large programs are where we need to have this automated analysis support. And OOAnalyzer just was not up to the challenge at that time. So this was obviously something that we wanted to make right. And so we set about trying to improve the performance inside of OOAnalyzer. Now, one of the things that you have to understand about OOAnalyzer's performance is that it very heavily relies on a feature that's called incremental tabling. And you can think of this essentially as memoization for Prolog. And the reason that's important is because OOAnalyzer is constantly trying to apply these reasoning rules, which you can think of as, if P, then Q. And essentially, if P hasn't changed at all, there's no reason to consider that reasoning rule because Q is going to be the same. It was either true or it wasn't. This has a huge effect on performance. And our original implementation of OOAnalyzer was built inside of XSP Prolog because it had a very mature implementation of incremental tabling, which we really rely on. So as you can imagine, we work quite closely with the developers of XSP Prolog, and one day they called us up and said, hey, we're working on trying to bring incremental tabling to a different Prolog system called SWE Prolog, and they wanted to use OOAnalyzer as a test case. And so that sounded great to us, being able to use OOAnalyzer on multiple Prolog systems, and so we agreed to help them out. It turned out this was a great decision and this benefited us in a couple different ways, but we didn't know that at the time. But one of the reasons is that SWE Prolog for our particular application turned out to be substantially faster than XSP just because of some of the design decisions and the properties of our particular application. But one of the other things that turned out to be very useful with SWE Prolog is it also has debugging and profiling tools that really allowed us to find the bottlenecks in OOAnalyzer and fix them so that we could start looking at larger and more complex software. So this is one of the tools that SWE Prolog provides, and it's called the resource timeline. And on the x-axis, it's basically showing you time progressing. And each one of these colored lines that you can see is showing you a different resource as it varies over time. So things like memory, the number of facts that we have at any point, the number of guesses, and things like that. The vertical black bars that you can see with the labels near them tell us which phase of OOAnalyzer is actually running at any given point. So this really gives us a good bird's eye view of how the analysis process is working and where we're spending the most time and resources. Now, on a more detailed level, SWE also provides access to a profiler. So like most profilers, it tells you, what functions are calling other functions, which you can see in a graph, how many times those functions are called, and probably the most important thing, if we zoom in here a bit, is it also tells us what percentage of our runtime is being spent evaluating different functions. And here, this is a big red flag. It's telling us that one particular rule, reason not merge classes Q, is using 1/3 of all the runtime of the whole system. And so that's an indication that we need to look at that rule some more and figure out why it's using so much time. So what actually causes these performance problems? Most of them were caused by fairly simple mistakes. Just because of the nature of Prolog, one thing that can happen is that if you order your clauses in a poor way, it can have some fairly negative performance impacts. But the flip side of that is that once you've identified the problem, a lot of times you can fix those performance problems just by reordering things. And that honestly is the case for a lot of the problems that we found. Unfortunately, it wasn't the case for all of them. We also found a more systemic problem. So remember, I told you that because of incremental tabling, If no dependent facts changed, we didn't need to recompute a rule, and that saves us a lot of time. But what I didn't tell you was what happened if one of the dependent facts did change. And the problem is that we actually have to recompute the entire rule, including instantiations of that rule that have nothing to do with the fact that actually changed. And the reason this is actually problematic is because some rules are actually pretty expensive to recompute. And essentially, over time, as OAnalyzer runs, we end up accumulating more and more facts, and so that means that the system ends up slowing down. And as we saw in MySQLD, this ultimately ended up to the point where we were essentially making no progress, even after running for days at a time. So our insight was that most of the rules at a logical level that we had are monotonic. And that essentially means that they don't need to be recomputed for new facts. The reason that they were being recomputed was because the Prolog implementation of tabling was just being a little bit conservative. So this actually inspired the development of a new type of tabling that's called monotonic tabling that's now part of SWE Prolog. And that has helped us speed up our code quite a bit. How much has it helped? Well, here's the before picture of our times, and the after picture is the red line at the bottom, and you can see that we're getting huge speed ups. In larger programs, we're getting 50 to 100 times speed ups. Remember I wanted to be able to run MySQLD in a reasonable amount of time, and now we're able to do that in enough time that we're still able to make an impact. If you remember this graph, right, we took 10 days of no progress when analyzing MySQLD. Now we're actually able to finish in about 33 hours. And just to give you an idea of how hot off the press these results are, since these slides have been made, we've actually brought that down to under 24 hours. So we're still making improvements and still making OAnalyzer run faster than ever. So, in conclusion, Corey and I have just told you about 3 very different projects that we have going on here at the SEI that are in 3 very different stages of the research lifecycle. We talked about some of our very early work on program reachability and how that early work informed us that there's not going to be a silver bullet solution, and we're going to have to continue that work in the form of a hybrid approach. We talked about our work on variable name recovery, which was initially a very early prototype that worked in theory but couldn't be easily used by analysts. We're now working on a plugin inside of the Hexraise decompiler that will allow analysts to literally receive better variable names at the click of a button. And finally, we talked about OAnalyzer, which was a tool that we had actually previously transitioned, and we talked about how it still had some limitations that prevented it from being used on large and complex software. We made it significantly faster, and now it can be used on much larger and much complicated software. So these 3 projects show that research is extremely important, but it also takes a lot of work to really bring research to see the light of day and have it be used by customers in practice. And that's exactly what we do here at the SEI. We take great research, we work on great research, often in collaboration with our partners on campus, and then we transition it into a form such that it can be used in practice. So I'd like to thank you very much for your attention. Corey and I would be very happy to answer any questions that you might have about these 3 projects, or if you have any questions about binary code analysis in general at the SEI, we'd be happy to answer those too. Thank you very much.
Hello, everyone. My name is Jeff Gennari. I'm one of Ed and Corey's colleagues here at the SEI. On behalf of us all at the SEI, I'd like to thank you for joining us for the research review. At this time, Ed and Corey are going to be available to answer some questions that you may have about their presentation. You can type into the YouTube chat. I'll act as the moderator, reading them aloud to you, reading them aloud to either Ed or Corey, who will respond in kind. So I want to start with some of the questions that, well, first, welcome Ed and Corey.
Thanks, Jeff.
Yep, good to see you guys. I want to start with one of the questions we received during the presentation. So Ed, this is from Greg, and it's about the variable naming or variable name recovery work. Is there a way to track the confidence of the neural network for a given variable name assignment?
Yes, that's a great question, Greg. So the way that the model that we trained actually works is that for each possible naming of a variable, the model is basically trained to give it a score. And then we basically pick the variable that has the highest score. So internally, you know, when you ask the system to give you a set of new variable names, you do get these scores along with it. So right now, we don't present that to the user, but you could imagine trying to use these to kind of have some kind of filter, so that if we have, you know, a really good name that we have a lot of confidence in, we're going to go ahead and maybe automatically rename those variables to the ones suggested by the model. And maybe if there's a variable that, you know, we don't have quite as much confidence in, we'll present it as a suggestion to the user, and then they can, you know, decide to use that variable name or not. One of the other things that's kind of nice about that is that, you know, we don't have to pick a single variable name. We could actually give the analyst the set of the top 10 variable names that we have the highest confidence in. And a lot of times, you know, that can give you a pretty good idea of what that code and what that variable is actually doing. One of the other things I wanted to mention is that it's actually a little bit hard to talk about what a good variable name is. So when we talk about confidence here, we basically mean our confidence that we've guessed the original variable name, but that's not necessarily a good predictor for whether it's a good variable name or not. And to get that kind of information, we really need to do some human subjects testing to basically see, you know, what do analysts really think about how good these variable names actually are that are being predicted by the system.
Thank you, Ed. We have another audience question that is about Prolog. It's from Corey, not this Corey, Corey Redfern. So trying to understand one of the main points with monotonic tabling in Prolog is the recompute speedup based on rules being unchanged except for some numeric variables. So I think we'll go with Ed as well here because he's been working mostly with the internals of Prolog and the Prolog developers.
Yeah, so that's another great question, Corey. So the way that we computed the speed up is really simple. You know, it's basically just a before and after. So when we say that, you know, there's 50 to 100 times speed up, you know, that's literally we ran OAnalyzer before and we ran it afterwards, and it you know, it's 50 to 100 times faster now. The speed up is actually coming basically from redundant work. So the real problem with the way that tabling worked originally is that as we would get a new fact, we would basically have to recompute the entire table or the entire rule over from scratch. And as you basically get more and more rules as the system progresses, that continues to get slower and slower and slower. And so the real problem was for the largest programs where basically, you know, we would compute a new fact, and then it would, you know, take on the order of hours before we could actually finish recomputing all those tables from scratch. So the speed up is really coming from that difference between, you know, computing everything from scratch and computing only the conclusions that could have possibly changed because of the new facts that we just got in the system.
And variable name work is very, people are intrigued. So there's another question related to that. Ed, this will be for you. The performance graph of the variable naming work makes me worry about overfitting. Any thoughts on that?
Yes. So, we did the normal approach of separating out our data into training, testing, and validation sets. So we have, we have pretty good assurance that we're not overfitting here because we're measuring based on our validation sets, which have, no intersection at all between the testing and training. In practice, we've been using this model more and more for experiments, and I could just tell you that anecdotally, as I talked about in the presentation, you don't always get the exact original name of the variable, and I would say, if you're looking at completely new code, it's not uncommon to get a different variable name, but what I've seen in practice is that you do get something that is very related to the behavior of the code that you're analyzing. So again, to me, as an analyst, that's really what I want. I don't really care if I get the original variable name exactly right or not. I just want something that tells me how that variable name is being used. And anecdotally, it seems like we were able to do that pretty well.
I'd like to change, if there's no other questions right this second, I'd like to change gears and talk a little bit about path analyzing. Corey, so that work was broad in that you evaluated many different foundational technologies, Pharos, Seahorn, Spacer. It encompassed a lot of things. So what is the future of that work? How do you take all these results that you've generated over the last few years and chart a path forward?
Thanks, Jeff. Great question. We're continuing to look at all of those techniques. We're maintaining the infrastructure in the Pharos system, the Pharos function summaries, and the weakest precondition code ourselves in the GitHub repo. But we're also continuing to look quite a lot at that new Ghidra plus Seahorn approach. As you know, because you were involved in the meeting last week, we had another conversation with Dr. Gerfinkel and his student just.
Great. And then Ed, there was a lot of interest in the variable renaming work. Maybe we can finish up by talking about the future of that work. It's very compelling and love to see it keep going forward.
Yeah, well, I think there's at least two directions where that work is proceeding to move forward. One direction is in the operational sense. So we're continuing to really work on a prototype of this and kind of get it to the point where we can just distribute it and get it into the hands of analysts. And the good news is that we're, as I mentioned, we're really close. We're getting there. If this is something that you're interested in, send me an email, and we might actually be at the point where we could start to have some beta users of this, or maybe alpha users more accurately. But I think this line of work in general, where we're using machine learning to study artifacts at both the source code and the binary level, and kind of learning the connection between how these works is a really interesting topic in general. So, in the talk that I just gave, we obviously use that to recover naming information, but you could imagine using that to recover all kinds of properties at the binary level as well. So some of the follow-up work that we're actually doing on this is to try to use that on this kind of same technique on another problem that's related to decompilation, and that is actually recovering type information from binaries. So decompilers like hexarrays, they often get really confused when you have complicated types like structs and classes and things like that. So one of the things we're looking at is trying to basically do the same thing of getting lots and lots of data, trying to train a neural network to be able to predict the types that are being used inside of these programs, and even going a little bit a step further and giving names to these types.
Well, great. So we're just about out of time. So thank you, Ed. Thank you, Corey, for the presentation and for the great Q&A. And thank you, everybody, for attending. I'd like to mention that we are going to go into a 15-minute lunch break right now before we return to the afternoon program. If you have more questions about Ed, Corey, or my work at the SEI, you can always reach out to us through email at info@sei.cmu.edu. Thank you again for your time. Enjoy lunch.
Welcome to the CMU SEI Research Review 2020.
If you had to pick one practice, one goal from this list, where would you start?
I'm going to let you go first.
Well, certainly from the, again, I'll tie this back to some degree to the insider threat work that we've done here at CERT. Establishing the appropriate level of privileges that individuals need to do their job, it's critical. It is an arduous process to keep up with the access controls, but it's essential to be able to provide the minimum level of privileges needed for an individual to complete their job and activities. And that does extend to your traditional employees, but also your trusted business partners, contractors, subcontractors, suppliers. Again, tying that back into knowing what assets people should have access to and verifying that only the people that should have access do have access to those assets and the capabilities that are associated with that asset.
Okay, so Randy, you would start with access control. Matt?
These are all like my children, right? So I worked with the folks that built this. So asking me to pick a favorite, number two.
Well, if you've had siblings, you know there typically is
yep,
a favorite.
Yep, and that would be me. So I would say identifying and being able to respond to risk is the most important thing. I need you to be able to frame risk for your organization, because that actually feeds just about everything else, right? How to build an incident response plan, you need to understand your risk appetite or risk tolerance. So if you're building a risk management program, being able to prioritize your risks will allow you to understand what sort of events are escalated to an incident response. It also lets you know how much network security and monitoring and so on and so forth. So I just feel like as if you understand your risk, you will be able to inform the other 10.
Yeah, so I'm going to start with the first item on the list. And I agree, all of these things are very important. And there's no right or wrong answer. But from my perspective, if you don't understand what the mission of the organization is, and you don't understand the assets, you can't apply the things you've described.
Agreed.
So I think for my dollar, I would start with understanding the mission and assets of the organization, understanding that the interplay of these things is ultimately what we're looking for. Right? There's not one that's going to bring you cyber resilience. It's really doing this in a way that's coordinated, that's integrated.
Hello, this is Ebony McNeil from CERT Division with your SEI Cyber Minute. Secure software is a top priority for many organizations. Static analysis tools output alerts that identify potential flaws in code. Last year, we publicly released Scale, an aggregator tool that displays multiple tool alerts and gives auditors an intuitive and user-friendly interface. Manually auditing alert determinations can often be time-consuming. We have developed a multi-server architecture and prototype system to integrate with Scale and other similar tools to enable automatic alert classification and advanced prioritization. We call the system the Source Code Analysis Integrated Framework Environment, commonly known as SCAFE. The SCAFE prototype is intended to be used by developers and analysts who manually audit alerts. SCAFE provides automatic alert classification using machine learning, which gives a level of confidence that the alert is true or false. The SCAFE prototype also enables organizations to apply formulas that prioritize static analysis alerts by using factors they care about. SCAFE relies on REST API principles to provide an interface for developers to quickly integrate and communicate with the server system. We have released the YAML formatted file specifying the SCAFE API, available at the CMU SEI GitHub for free downloads by the public. The YAML specification provides the SCAFE API definition beta version in a format that developers can easily use to view, modify, and automatically generate code from. Thanks for watching this SEI Cyber Minute. For more information, please visit our website or send me an email at info@sei.cmu.edu.
And at this sort of moment where we're thinking about a new normal post global pandemic or coming out of the global pandemic, the time just seemed really right to do this, and particularly to think about your area of expertise, which is humans and organizations within it. So I was really wondering if you could start us off by telling us some about the research you're currently doing and the projects you're currently involved in.
Yes, well, thank you. And you're right. This is an inflection point. It is a time for us to think about what have we been doing in the past and how can we really adjust. And for me, what has really taken hold is this idea that we can no longer sit in our stovepipes and look at problems from isolated disciplinary lenses, but we really have to think across and to think about the whole of the problem and how different aspects of that can be addressed. And so the work that I'm doing is really a continuation of what I've been doing for many years, and that is thinking holistically about how to develop global cybersecurity workforce capacity, thinking about not just developing the technical capabilities, but how do we do that within the context of actual work requirements, and thinking very critically about how to get people ready to hit the ground running. And so that includes human factors and how they interact with other individuals, how they deal with the environment, but it also includes a forward leaning to think about, as we move into these virtual spaces because of the pandemic, how do we leverage technology? How do we integrate human behavior with automation and things like that? And so really, it's an opportunity for me to bring all of these different conversations to bear about the future of work, about the global cybersecurity workforce, and to really leverage that work to give us a good starting point to move forward.
So what sparked you into this, right? I love the interdisciplinary and multidisciplinary nature, right? Because it's both, as you point out.
Yeah.
What got you started?
Well, I'm going to have to give all credit, and people will think that we've set this up, but this was really encouraged in my graduate study at Carnegie Mellon. My interest, my passion has always been on looking at a problem. And really what encouraged me were the faculty members at Carnegie Mellon that said, this is how we as an institution move science forward. It's by thinking about the whole of the problem, but developing disciplinary expertise so that we can effectively address these problems. So that has really been the impetus behind my work. It was my natural tendency, but it was certainly encouraged by my education.
Thanks for the plug. We actually didn't set that one up, but Carnegie Mellon's a little bit of a special place there, right?
In an exercise or simulation, there are players, human cybersecurity operators. Other roles are controlled by a computer. These are non-player characters, or NPCs. Ghosts is that computer platform that orchestrates friendly, hostile, and every type of NPC in between that our players would encounter. The solution to orchestrating complex and realistic cybersecurity exercises with many computer-controlled roles is our Ghost platform. Ghosts create realistic network traffic, but is not traditional user sim. It is not simply a mechanism for traffic generation. It avoids creating generic packets on the wire that have no context or do not map back to specific user activity. Rather, Ghosts provides context-driven user activity on a network because it focuses on what every computer-controlled NPC on the network is doing, what decisions it might make, and uses the results of those decisions to make every future decision as well. In essence, Ghosts brings harmless administrators and hostile red team operators to life within an exercise. Ghosts give them growing intelligence and mimics what people may do in real life. With simple configuration files, clients can be pre-programmed to perform a random series of tasks throughout an exercise, specific activity at a point in time, or infinite combinations in between. From the control server, you see and control all of your MPC activity in real time, with rich reporting dashboards and actionable intelligence. Blue team players want to show that they can defend their terrain and the users within, even when those users are unpredictable and subject to making wrong decisions that affect more than just themselves. What this means is Ghosts enables exercise creators to build enclaves of blue teams that perform specific tasks. The system also provides the ability to simulate active insider threat scenarios, or simply random security mistakes that any user might be unfortunate enough to make, such as falling for a phishing attack or similar situations. On the other hand, red team players want to simulate large-scale attacks, coordinated efforts up and down the kill chain, and be able to adjust to defenses. Ghost provides Op4 players with these abilities via a scriptable interface that they can use to control a large-scale NPC team that performs distributed and/or dependent tasks. As an example, denial of service attacks including hundreds of machines can be created and modified as defenders take steps to mitigate its impact. In a sense, Ghost is an on-demand bot army for red teams. In building and delivering effective cybersecurity exercises, we have found that the key ingredient to maximizing value is realism. Ghost is a solid framework for creating great scrimmages with all the necessary teammates and opponents so that teams can practice their way to becoming elite.
Hello, this is Chris Alberts from SEI's CERT division with your SEI Cyber Minute. A threat modeling method is an approach for creating an abstraction of a software system, profiling an attacker's abilities and goals, and identifying possible threats that a software system must mitigate. Examples of common threat modeling methods include stride, trike, persona non grata, and misuse cases. For the past several years, my colleagues and I have developed, piloted, and refined the Security Engineering Risk Analysis, or SERA method, a risk-based approach for evaluating mission assurance in system-of-system environments. The SERA method incorporates a variety of models that can be analyzed at any point in the lifecycle to identify threats and vulnerabilities and construct cyber risk scenarios. Recently, we started exploring how to integrate threat modeling methods into the SERA method's mission assurance scope. We can use cyber threat data generated by threat modeling as the foundation for developing serious cyber risk scenarios. If an organization does not have a preferred threat modeling method, it can use the SERA method's threat modeling component to generate the required cyber threat data. Thanks for watching this SEI Cyber Minute. For more information, please visit our website or send me an email at info@sei.cmu.edu.
Good afternoon. I'm Bob Sheila, the Technical Manager for Secure Coding at the Software Engineering Institute. For more than a decade, we've been researching tools and practices to implement secure software. That is, software that is built not to have security flaws. Our work has led to the development of our secure coding practices and secure coding guidelines for languages like C, C++, and Java. Our work has also led to tools and practices for auditing software source code to identify and mitigate security flaws. More recently, we've extended our research into new approaches to improve the efficiency and efficacy of security flaw resolution. Software defects are a part of the nature of software development. Software is developed by people, and often the layers of abstraction and simplification that we put in place might make it easier to develop software, but it also increases the possibility of defects as the designers and developers' intent is translated into increasing levels of detail down those layers to concrete executable code. Each layer has to make assumptions as it fills in the blanks of the implementation that were lost in the abstraction. As software has grown in size and complexity, the challenge to find and fix software security flaws has become insurmountable. And the challenge of fixing security flaws in legacy software that is fielded presents a whole different challenge when there aren't resources dedicated to sustaining that software. Over the next hour, you will hear from two of our top researchers about our recent work to address these problems. First, Will Kleber is going to talk about our latest work in automated code repair. For the past few years, we've been researching how to automatically repair source code for specific types of common security flaws. The motivation is to not just use tools to report security flaws that analysts and developers have to verify and repair. Instead, use tools to modify the code safely, or in worst cases, provide repair options and identify the need to add custom error handling. This automated code repair can be especially helpful to those responsible for the security of legacy code that don't have teams of resources to find and fix security flaws with standard analysis tools and practices. This year, we completed a project focused on repairing code for memory safety. And because people often use programming languages like C specifically for performance, our work is also focused on measuring and minimizing overhead performance costs for this memory safety. After that, Lori Flynn is going to talk about our research in improving the efficiency of source code static analysis by applying machine learning methods to improve tool performance. Source code analysis has theoretical limitations on accuracy. Tools cannot identify defects perfectly. Either they will miss defects and not report them, or they will misidentify defects that are not actually problematic. Or, most of the time, tools will do both. For that and other reasons, it has become a commonly recommended practice to use multiple tools, as they each will have different strengths. But this approach will usually find more reported defects that can be manually adjudicated and fixed. So for the past few years, we've been researching how to apply information from past alert adjudications, or as we call them, determinations, to provide a confidence that new alerts are likely true or false. This can provide a new efficiency of how alerts are approached and resolved. At the end, Lori will also talk about how you can incorporate both of these technologies into your software development lifecycle processes. Lori will also be talking about our work this past year in this area in more detail in a later research review session. I hope you enjoy the presentations as much as we enjoyed the research. During the presentations, we will be watching and responding to questions and comments on the YouTube chat. After the two presentations, Will, Lori, and I will be available to answer questions in a live Q&A session. Thank you for joining us. And now, Will begin his presentation on automated code repair.
Hello, my name is Will Kleber. Today I will talk about automated code repair to ensure memory safety. Software vulnerabilities constitute a major threat to DoD. Spatial memory violations are among the most common and most severe types of vulnerabilities. They constitute 15% of the vulnerabilities found in the NIST National Vulnerability Database and 24% of critical severity vulnerabilities. Last year, a vulnerability was discovered in the iPhone iOS that allowed an attacker to remotely take control of the phone whenever the user visited a malicious website. This vulnerability was exploited by the Chinese government, according to TechCrunch. A similar vulnerability was discovered in the Android stagefright library. An attacker could send a malicious MMS message to a vulnerable phone and thereby take control of the phone. The Cloudbleed incident is interesting because there was no active attacker. The Cloudflare web proxy, under certain conditions, would read past the end of the buffer and return potentially sensitive information. This information was sometimes cached by search engines such as Google. There is a huge volume of code in use by DoD with an unknown number of vulnerabilities. Our solution to this problem is to automatically repair source code to assure spatial memory safety. We insert code to abort the program, or call an error handling procedure, immediately before a memory violation would occur. This prevents the program from being exploited by an adversary. In our approach, we transform the source code to an intermediate representation, an IR, while retaining the mapping back to the original source code. We then repair the program at the IR level to use fat pointers to track bounds, and we insert bounds checks before memory accesses. We then map the repairs at the IR level back to source code. As input, our tool takes a buildable code base written in C. As output, it produces repaired source code that is still human-readable and maintainable. We envisioned that our tool would be used before every release build and used occasionally for debugging builds. Our tool is intended for ordinary developers, and no special knowledge of static analysis is required. Our tool can be used as part of a DevOps toolchain for new code, and it can also be used to repair legacy code. So, why do they repair at the source code level as opposed to doing the repair as a compiler pass? One reason is that repair done at the source code level is easily audited if desired, whereas with repair done as a compiler pass, you kind of have to trust the tool. Secondly, repairs that are done at the level of source code can easily be tweaked to improve performance if necessary. Whereas with a compiler pass, it is difficult to remediate any performance issues caused by the repair. Third, doing repair as a compiler pass involves changes to the build process, and these changes might be difficult and error-prone, especially in the long term, because they create unwanted dependencies. Fourth, repair at the level of source code can be done as an offline process so that it can conduct a slower, more precise analysis. There is a gap between static analysis to detect bugs, which works best at an intermediate representation, and repair on the original source code. The difficulty is to translate the repaired IR back to source. We address this with the pipeline that we show on the next slide. In the first step of our pipeline, we translate the source code to an abstract syntax tree, an AST, while retaining a mapping between the source code and the AST. In particular, each node of the AST is annotated with the name of the file that it came from, as well as the beginning and ending byte offset. In step 2, we translate the AST to an intermediate representation while recording a mapping between the AST and the IR. Then in step 3, we perform analysis and repair at the IR level. In step 4, we map the repaired IR back to an AST. And this step is sound by construction, meaning that we guarantee that we preserve semantics between the repaired IR and the repaired AST. In step 5, we map the repaired AST back to source code. If the AST node is unchanged, then we simply reuse the original source code text. If the AST was changed, then we generate new source code from the AST. We replace raw pointers with so-called fat pointers. A fat pointer is a struct that includes the pointer itself as well as bounds information. Before dereferencing a fat pointer, a bounds check is performed. For each pointer type, we introduce a corresponding fat pointer type, which is defined as a struct with 3 fields. The first field, RP, is simply the raw pointer itself. Base is the base of the memory region, and size is the size of the allocated memory region in bytes. Fattening of pointers has previously been performed as a compiler pass. We built on this work and extend it to be able to perform this fat pointer repair on source code. Let's consider an example of a program that contains a pointer P that points inside of a string. In our repair, we convert P to be a fat pointer. P.RP points to the same location as the original pointer. P.base points to the start of the allocated memory region. And P.base plus P.size minus 1 points to the last byte of the allocated memory region. Now let's consider an example of what the output of our tool looks like. Here we see an original piece of source code as well as the repaired version. First, our repaired tool inserts pound includes for the header files that define the fat pointer types as well as operations on those fat pointer types. On line 7, our tool converts the char pointer to a fat pointer. It also converts the memory allocation function malloc to be the corresponding fat memory allocation function. And that fat malloc function, what it does is it basically calls malloc and then wraps the results in a fat pointer. On line 10, a bound check is inserted immediately before the pointer dereference. On line 11, the pointer arithmetic is converted into a function that performs the pointer arithmetic on the raw pointer components of the fat pointer. For each pointer type, we define a wrapper around malloc. This fat malloc function, what it does is it calls malloc, and then it wraps the results in a fat pointer, initializing the 3 fields of the fat pointer: RP, base, and size. One thing to note is that malloc can fail. If malloc fails, then it returns null. We insert a special check to check if malloc failed, and if it did fail, then we set the size component to 0, and this indicates that no memory was allocated. We also introduce fatp_add functions for each type, which perform pointer arithmetic on the raw pointer components of the fat pointer. Alternatively, we can introduce a single macro that works for all functions. The disadvantage of this macro is that it requires extensions to C, and these extensions are widely supported among compilers, but they are not universally supported. The major benefit of this macro approach is that the name of the fatb add function is shorter because it does not need to include the type in the name of the macro, and thus it leads to less code bloat. The bound check function, what it does is it checks to make sure that the row pointer component of the fat pointer is within the memory region defined by the base and size components of the fat pointer. If the row pointer component is outside of those bounds, then what our tool does is it aborts the program. And again, this function can be defined either as a separate function for every fat pointer type, or it can be defined as a single macro. We ran our tool on 52 memory safety benchmarks in the SVComp benchmark suite. To verify the efficacy of our repairs, we ran Symbiotic, which is a widely used software verification tool, on the original and the repaired files. On the original files, Symbiotic was unable to prove that any of the files were safe, and it was able to prove that 48 of them were unsafe. On the remaining 4, it was unable to determine an answer. On the repaired files, Symbiotic was able to prove that 27 of the files are now memory safe, and it was unable to prove that any of them were unsafe, and for 25 of them, it was unable to make a determination of whether the program is safe or unsafe. We tested our tool on bzip2, a widely used compression program. Across a variety of file sizes, we get an overhead of approximately 50%. So our DoD collaboration partners said that this 50% overhead is too high for many of their use cases. So that raises the question, can we significantly reduce this overhead while still being able to prove memory safety? And the answer is probably we aren't, but automated repair is still valuable even if we fix only the most likely bugs. So, in order to get an acceptable overhead time, we added an option to insert bounds checks for only those memory accesses that are warned about by an external static analysis tool. And this reduced the overhead to only 6% on bzip2, which is much more acceptable than a 50% overhead. We cannot guarantee memory safety in the presence of non-standard pointer tricks, such as XOR-linked lists, reuse of memory for different types, except via unions, which we do support, concurrency, because race conditions can cause memory corruption, and external code that accesses program memory. If a program's data structures are accessed by external binary code, then the pointers inside of them cannot be fattened, because that external binary code, it relies on their program having its original memory layout, and if we change that memory layout by fattening the pointers, then we break the external code. So we identify those pointers that are accessed by external code, and to do that identification, we use a whole program points to analysis with an allocation site abstraction. So now I would like to discuss in more detail step 5 of our pipeline, and that's the step where we map the repaired ASD back to source code. So to do this, we implemented a modification to Clang to extract a source ASD mapping. In translating the repairs from the repaired ASD to repaired source, the main source of difficulty is the C preprocessor. So if we need to make repairs to macro uses, what we do is we expand out the macro and make the repair to the expansion. For repairs to pound included code, what we do is we just repair the pound included file. For conditional compilation directives such as pound ifdef, pound endif, if those occur inside expressions, then we need to make sure that our repair preserves those so that it doesn't produce syntactically incorrect code. When an expression or statement is repaired, what we do is we generate new code for the repaired portion of the AST, and for the portions of the AST that are unrepaired, we simply reuse the existing source code. The C preprocessor can conditionally include or exclude pieces of code depending on the configuration that is chosen at compile time. And here, by configuration, we simply mean the values that are assigned to the symbols used in the preprocessor directives, such as pound ifdef. We repair the configuration separately, and then we merge the results together so that the final repaired code is correct for all desired configurations. If a line of code is repaired differently for different configurations, then each version is included, guarded by appropriate conditional directives. Here we see an example of how we merge multiple build configurations. In configuration 1, the symbol useLong is defined, and we fasten the long star pointer. In configuration 2, the symbol useLong is undefined, so we fasten the int star pointer. Then we merge together configurations 1 and 2 so that in our final merged results, all of the pointers have been fastened. We say that an operation is idempotent if applying it once has the same effect as applying it multiple times. Ideally, we want our repair operation to be idempotent. That is, if a code base has already been repaired, then applying the repair operation again should have no effect. However, we are not at that point yet. So, to avoid double fattening, what we do is to introduce a defattening operation. This defatten operation, what it does is it takes all of the fatten pointers and converts them back to raw pointers. Then we can apply the repair operation again. So the composition of repair and defatten is idempotent. The project team for this project consists of myself, Ryan Steele, Matt Chirilla, David Svoboda, Mike McCall, and Ruben Martins. In conclusion, our tool repairs code bases to ensure memory safety. It does this by converting raw pointers to fat pointers. The user can select one of two modes of operation. In the first mode, our tool makes all possible memory repairs. This incurs a larger overhead, for example 50%, but it is able to guarantee memory safety, at least in some cases. In the second mode, our tool repairs only likely memory violations, as flagged by an external static analysis tool, which incurs significantly less runtime overhead, but does not provide any guarantee of memory safety. We are happy to provide our tool to any interested parties. It should be noted that this is a research-grade tool, not a production-grade tool. Further development work is of course possible to suit particular needs. In the long term, and with further development, DoD can use this technology to ensure memory safety as part of all software projects with code written in memory unsafe languages, such as C and C++. For more information, please contact me at the address shown on the slide. There is also a blog post that contains more information about this project. Thank you for your time.
I'm going to talk about line-funded research projects that I've led starting in FY16 through FY20 on the topic of static analysis classification. Each project in those 5 years of research have built on tools and techniques developed from the previous project. For more details on my FY20 project, please attend my Friday research review presentation. At the end of this presentation, I'll include ideas that Will and I have for combining his automated code repair techniques with the classification techniques that coming from my research. Throughout the following slides, you'll see these 5 icons which highlight research focus areas. On slides where there is a red rectangle around the icon, that topic applies to what's discussed on the slide. So today, code bases are run through one or more static analysis tools, each of which outputs a set of static analysis alerts. Now let's break to focus on the definitions on the top right on this slide. An alert is a static analysis warning that has a checker ID, a line number, file path, and a message. An alert condition is an alert mapped to a type of a code flaw. And a meta alert is mapped to by the set of all alert conditions that differ only by checker ID. Alert conditions from different tools can map to the same meta alert. In this in all of my projects, we do adjudication true false and automated classification at the meta alert level. So back to the figure on this slide. So today, manual adjudication is required, resulting in a chart like that shown at the top right, where a small number have been manually adjudicated true positive and false positive, but the vast majority are shown in that big red bar where they're indeterminate. They haven't been examined. There may be true positives in there. There may be severe code vulnerabilities that we're warned about. The goal of all of the projects is to enable practical automated classification, accurately classifying meta alerts as expected true positive, expected false positive, and a small number aspirationally as indeterminate. Aspirationally, that number would be small enough that there would be enough effort to be able to manually adjudicate them. So the next 2 slides will cover 5 years of research, and then slides after that will go into more detail. So in summary, in FY16, the issue that we addressed was classifier accuracy using the novel approach of using multiple static analysis tools as features, the tool names. This resulted in increased accuracy using our 10 years of CERT audited data. In FY17, we addressed issues of data quality and of having too little labeled data to develop accurate classifiers for some types of code flaws. The novel approaches that we used, there were 2 of them. One involved developing audit rules in a lexicon. The other involved using test suites in a novel way to automate the production of labeled true-false meta alert data for many types of code flaws. Test suites were originated to test for coverage of types of code flaws and precision for static analysis tools. So this labeled data generation was novel. Using our data set plus data from 3 DoD collaborators, this resulted in high precision for more conditions. In FY18 to 19, the issue we addressed was that there was too little use of automated meta alert classifier technology because it requires a lot of money, data, and experts to set up such a system. Our novel approach involved developing an extensible architecture. As a result, we've enabled wider use of classifiers with less starting money, data, and experts with what we've developed, this extensible architecture, API, software to instantiate it, and active learning or adaptive heuristic research. In FY20, this is the first year of, we're ending the first year of a 2-year project. The issue that we're addressing is that it takes too much time to adjudicate static analysis meta alerts during continuous integration, or CI. The novel approach involves using classifiers during CI builds with precise cascading, which I'll describe later, and using additional features, including CI/CD features, semantic features, and more, and some active learning research. We have a lot of results from this year so far, including a design for CI/SCAFE system integration, some empirical results on diff-based cascading, which I'll detail later. So one of our initial research focuses involved developing an audit lexicon and rules to improve data quality. Developing classifiers starts with selection of a candidate code bases for evaluation. Then static analysis and other tools are run on the code bases. We convert that data to meta alerts and associated data, and humans evaluate. They make adjudications on some of the meta alerts. Then the labeled training data is used to build machine learning classifiers that predict true and false on the remaining meta alerts that haven't yet been manually adjudicated. But back up, what do true and false mean? And are there other determinations that could be used? So in examining the research literature and the industry literature, it turned out that there was no widely accepted auditing lexicon and auditing rules. For example, one of our collaborators used true to indicate that the code flaw indicated, like CWE 190, actually did occur at that point in the code. Another collaborator used the determination true to indicate that something was wrong at that line in the code, even if it was different. However, inconsistent assignment of audit determinations like true harms the quality of the classifier. So we developed this lexicon and auditing rule set. It includes a set of auditing rules to help auditors make consistent decisions in commonly encountered situations as well as corner cases. Next, I'll talk about classifier development data and tools that we've developed in architecture. So SCALE is a static analysis meta alert auditing framework that has been developed by the SEI for about 10 years. It has a GUI front end for examining meta alerts and associated code, and meta alert adjudications and other data are stored in a database. We use it for research projects and used it throughout this 5 years. We enhance the framework with features for research, and collaborators use it on their code bases. And then us researchers analyze the audit data. One of the important features that we added is an archive sanitizer that enables especially DoD collaborators to share data that might have some sensitive fields. For instance, possibly sensitive fields could include function names, project file names, namespace package, etc. We anonymize these fields using a SHA-256 hash with a salt that the collaborator keeps the salt private to keep it a one-way secure hash, yet enable us to analyze the features correlated with meta alert confidence for classifier development and application. Data, CERT audited data is something we've used for classifier development. We have about 7,500 audited meta alerts plus data from 3 DoD collaborators. When we analyzed our CERT audited data archives, we found that although we had 382 CERT rules at the time, we only had labeled true-false data for about 158 of those. And furthermore, for many of those rules that we did have data for, it was only one way, only true or only false. All of that harms the ability to create good classifiers. So that motivated my idea to use test suites in general to generate labeled data. Our initial generation of about 38,000 labeled alerts was a big savings. A manual audit of any 38,000 meta alerts from natural, not test suite programs is estimated to take about 1,200 hours, using 117 seconds per meta alert audit, taken from the Google Find Bugs Fix It large study. However, it would be unlikely that that set of meta alerts would cover many of the code flaws that are covered by the Juliet test suite, because it was created to specifically cover many flaws. And further, we needed both true and false labels for classifiers. So realistically, a hugely larger amount of effort would be required to develop so much data. Now let's talk about the SCAFE modular architecture that we developed starting in FY19 that enables static analysis meta alert classification. Our DoD collaborators have told us that they want an architecture that is able to adapt to different systems and tools. And further, they want an architecture that not only we can adapt to different systems and tools, but that they can. So we developed SCAFE and the API to fit those requirements. The SCAFE API formally defines interfaces between modular parts, and the SCAFE systems are software systems that instantiate the API. We use the Swagger Open API toolset, an open source toolset for developing the formal API definitions. That includes Swagger tools that automatically generate client and server code from API definitions in a wide variety of languages. The SCAFE architecture is shown on this diagram. This is our FY19 architecture. You can see that there are 5 modules. The most important one to focus on is the UI module at the top. Any static analysis tools can instantiate APIs to become a UI module and to then be able to use classifiers. The statistics module at the bottom right is the one that creates, runs, and stores classifiers and does adaptive heuristics or active learning. So the SCAFE formal definition allows users to efficiently start to use classifiers with a wide variety of systems and tools, and the instantiated system does even more so. In FY20, we modified the design to enable classifier use during continuous integration. You can see the CI server at the bottom left, and many API calls are new or modified. And in the code base, we've modified the code as well. So the next slides are provided with software artifacts from FY18-19. They're provided as a resource for viewers who are interested in accessing papers and code and data produced during those years. I'm not going to speak to them, but if you're interested, they're available on the slides. Next, I'll talk about the FY20 project in a little more detail. So the CI workflow is shown on the bottom or on the left here, where a member of the development and test team develops a code branch with a bug fix or a new feature, and they check the source code in to a source code repository, and then the CI server takes that code and runs tests on it. Usually the automated tests, it's a set of regression tests. Usually they include unit tests that look for, that check to make sure that small bits of functionality still work. Then there are integration tests, which check to make sure that different parts of the code still interact as they should. And often there are stress tests that make sure that the performance hasn't gotten worse. Sometimes, not always, sometimes a static analysis tool or two are run automatically during this process. If that happens, then then a set of static analysis alerts are produced. Usually there are a lot of them, and all the results of the testing get sent to the development and test teams. If all the regression tests pass, usually the development and test teams want to quickly merge that new code into their development code branch. That way all new code, all the new branches that they're working on can start to use that code. And so that their code won't have merge conflicts with it. So there is not much motivation for them to spend much time auditing the static analysis alerts. And furthermore, as the code continues to get developed, often a lot of the static analysis alerts, if you run the same tool on the code base as it grows, you'll get a lot of the same initial static analysis alerts, but then you'll get more because the code base has grown, and that keeps on happening more and more, and the issue of trying to deal with all those alerts gets even worse. So those are, that's the outline of issues that this research addresses. One of the aspects that we're working on in FY20 to 21 involves precisely cascading adjudications from previous code versions. When you run the same tool on different code versions, you get sets of alert conditions from each. If there were manually made adjudications false positive previously, then the question is, how do you match the meta alerts? How do you decide which false positives should cascade forward? If you do it imprecisely, using just file-based and syntax-based cascading, you may incorrectly cascade too many false positives and miss a true flaw that was warned about and mislabel it. That not only can make you miss that flaw, but it also can harm your classifier results based on that labeled data. So in FY20, we've generated data using diff-based cascading, imprecise cascading on an open source code base. And in FY21, we'll compare that to precisely cascaded data. We've released multiple API and software artifacts during FY20. The reason that we've done so many releases is because we want to get feedback from collaborators as soon as possible as we're developing to improve our systems. Detail on the select artifacts and links to various artifacts, including presentations and papers, are provided here. We invite you to collaborate, especially DoD organizations that do CI development. I need you to test our tooling. The current collaborators test, but they're not doing CI development themselves. The full system implementation release is currently limited to only the DoD. CI testing does not have to include data sharing. If you're interested, please contact me. We support deployment and testing. The release system is containerized, and we have configuration files that make for easy modification of ports, URLs, host names to ease integration in a wide variety of systems. It comes with extensive documentation. We've expanded that a lot this year. And part of the FY21 project is designed specifically to help collaborators use the system. If you could help us get labeled data, we'd be grateful for that as well. The next slide provides self-training resources for auditing meta alerts. In the near time frame, the public can use and review the SCAFE API and the SCAFE Scale module. We just released on September 30th the SCAFE version of Scale on GitHub. It's a SCAFE Scale branch. And DoD collaborators will continue to test and provide feedback throughout FY21. Beyond that, we hope that we'll be able to make design improvements for transition to improve performance and to harden security and to add to scalability. And in the long term, we hope that this research will enable practical automated classification for more secure software at a lower cost. My FY20 project team is here. And for more information, please contact us here. Next, I will talk about Will's and my ideas for combining meta alert classification with automated code repair. So let's see. So there are two options for using ACR in this combination that we're talking about. So they're both the green boxes. Both of the green boxes show those. So looking at this figure, please look at the top where you see the source code. And just to the left of that, let's say a new feature development or bug fix gets merged into the source code. Right after that, you have the option 1 of doing automated code repair. If you use that option, you make all possible automated repairs. This has a worse runtime overhead than option 2, but better safety. Next, or instead of, you do meta alert classification as I've been describing on the previous slides. Run static analysis and other tools, run your classifier, do active learning. Then your system splits the results into 3 categories: expected true positive, expected false positive with a high confidence, and indeterminate of prioritized meta alerts. And then split off a 4th category of high priority expected true positives that you're able to make automated repairs on. So here we do option 2, where you only repair higher priority meta alerts. This has less runtime overhead, but it might leave unfixed vulnerabilities. For the expected true positive with high confidence, those that can't be automatically repaired, those go directly to manual code repair to a developer who works on them in parallel. For the ones that are indeterminate, those are prioritized and taking each from the top. The human adjudicator adjudicates true or false. The ones that they adjudicate false, they go into the ignore bin. The ones they adjudicate true go straight to the manual repair, code repair developer. The repaired source code now goes back up to the top of the diagram, and the process continues. One vertical flow could happen in this diagram could happen during one continuous integration build cycle, where the system cycles until the build passes and then repeat each build. Or it could happen, or a vertical flow could happen during a code security analysis and fix. So Combining such systems is a concept that Will and I envision. However, research and testing would be required to develop a practical automated or practical integrated system. Now we welcome your questions about this combined research, about Will's research on its own, or about my research on my own.
So now we're going to start with some questions and handle any questions you might have had through Will and Lori's presentations. I'm going to start us off with a question that continues the last couple slides there about merging or combining ACR with the classifier work. And so I'll ask Lori and Will, where are we and are your thoughts on what needs to happen or what could happen both with research and with development or with implementation with regard to merging them and how they would be able to help people in their development life cycle? So Lori, you want to start off?
Sure. So both of us, our teams have developed prototype tools. So we have a lot to start out with. With the design that we just showed, we think that would take mostly software engineering, but to make it a practical system, measures of the different latencies and consideration and analysis of ways that performance could be improved could make such a design much more practical. And since that kind of a combination is a new thing, that would basically be a case study and would be research. So there's both research and a lot of software engineering involved.
Okay, Will, did you have anything to add?
No, I think Lori covered it.
Okay, great. Now we do have a couple questions from the audience here. So first one from Patty, and I'm guessing this is for you, Will. So is the overhead and longest runtime worth the return on investment?
Right, so I guess that depends on the particular needs of the customer. For many customers, I think making sure that you do have reliable code that does not have any vulnerabilities is definitely worth it. Now, in some cases, you can't really tolerate like a 50% overhead, so we do have that option to only repair memory accesses that are flagged by a static analyzer. So I would say that at least one of those two options would give you a desirable return on investment. Like, I guess some customers would prefer the slower one because it gives you better guarantees of memory safety, but if you can't tolerate the slowness of repairing every memory access, then you can just fix the ones that are most likely to have bugs.
Okay, thank you. We have another question here, and this one is for Lori. Regarding meta alert classification, what ML algorithms are you using? And can you say more on your approach to online learning? I'm guessing that's about the audit learning, but if that's not, it came from Maygems. If you could add what your thoughts are on online learning. But yeah, so Lori?
Yeah, so in our current instantiation of SCAFE, we've got 3 types of classifier that we use. One is random forest, one is XGBoost, and we're also doing logistic regression. However, we've developed the system in a modular way, so different types of classifier development can be used. Now, with respect to active learning, that is an active area of research that we're working on. So the combination, let's see, so as the system is functioning, and more data is aggregated, more manually adjudicated meta alerts are produced, more test suite data is created, etc. We think that the system can improve, and based on the type of projects the particular organization develops, we want our system to tailor itself to that kind of data. So we're working to improve our active learning heuristics using some techniques that are standard for, using some techniques from other people's research on cross-project learning, cross-project classification, and doing some unique active learning research related to test suite versus non-test suite data especially.
And the online learning, do you have anything to add to that?
Oh, I was interpreting that as active learning.
Oh, okay. I thought you were talking about the classifier. Sorry. Okay. So yeah, may just, if you can add a clarification if that didn't answer it, we'll cover that question. I'll try and squeeze a couple more in here. We just have a couple more minutes. So Will, your ACR work that you presented largely focuses on C. What would it take to enable it to repair C++ code?
Right, yes. So I would say that the biggest challenge for handling C++ code would be repairing template definitions. And in some aspects, though, C++ would actually be easier than C because we can use C++ features in our repairs. So we could make a fat pointer class and overload its operators. So it's kind of hard to estimate how long it would take to handle C++, but I would say probably between like 3 and 6 pursuits of effort should be enough to extend our work to C++.
Okay, great. And we did get confirmation from Mejabis that that you did cover it, Lori. So thank you. I completely misinterpreted the question. Thanks for covering that. And a question for both of you. I know that you sort of covered this in your presentation, but if there's anything else you'd like to add with regard to people getting access to your tools. So Lori, what can people do to get access to either your tools or the information and knowledge that you've gained through the research?
Okay, great. So let's see, for the full SCAFE system, with the 5 modules and everything, currently we're only allowed to release that to DoD collaborators. So if you're DoD, just ask me for it and I would be so happy to have you use it, test it. Right now, parts of the rest of our system we can release publicly on SEI's GitHub, public GitHub. We have the full SCAFE, the full scale system, which is the separable user interface module for adjudicating meta alerts without the classifiers. But it's got the API calls for the rest of the SCAFE system, and we've published our SCAFE API. So automated code generation can help folks to develop the rest of the code system, develop the rest of the SCAFE system on their own for the other 4 modules. Beyond that, we've got lots of papers, presentations, and blogs on SEI's website.
Okay, great. Do you have anything special other than contact us to add, Will, about your work?
No, I think if anyone would like to have the ACR tool, just contact me at the email address shown on the slide, the info@sei.cmu.edu email address, and I'd be happy to share the ACR tool.
Great, thanks. You actually took my wrap up, which was, yes, as Will just said, if there's anything further that you'd like to get information on, contact us at info@sei.cmu.edu. And I hope you enjoyed the presentations and the QA. And thank you very much. Have a great rest of the day and enjoy the research review. Take care.
Hello again. Roman Danilou here as the SEI Deputy CTO. Scalable approaches to identifying software vulnerabilities and automatically assessing software behaviors is a core area of research at the SEI. You just heard 4 back-to-back sessions on research that improves the efficacy of static analysis in source code. This kind of analysis is a foundational element of test and evaluation regimes of any software factory operated by a program office. It provides the basic confidence that software has fewer known vulnerabilities. This provides some evidence as well to enable the basis of continuous authority to operate, continuous ATOs, and adopting these approaches reduces the cost to find those vulnerabilities and to remediate them. In revisiting the first talk you heard on that analysis from Dr. Will Kleber on automated code repair, that was focused on the next step in assurance. It's about moving beyond simply identifying vulnerabilities to moving beyond those vulnerabilities and asking programmers to fix them, but also showing that in particular domains that the code can be automatically fixed. In the next talk from Dr. Laurie Flynn on static code analysis, this focused on a practical solution software factories are currently facing when they use multiple analyzers simultaneously. The data shows that you get better coverage from using multiple analyzers to find more vulnerabilities. However, using more analyzers generates more duplicate alerts and also increases the overall alert volume. And so this field-tested research says that by using a meta-analyzer, you can synthesize those related alerts and really realize the benefit of having multiple analyzers while having to deal with the same alert volume. Finally, in the third talk, again by Dr. Flynn, about integrating static analysis kind of systems into a CI/CD pipeline, this focused on another challenge where you have a continuous check-in stream of updates and automated analyzers are continuously triggering alerts on the same code that's going into the code repository. And what this research allows program offices to do is not to have to turn down the sensitivity of those analyzers and really can continue to find those vulnerabilities up to the capability of the tools while still allowing an automated process that gives new features through a CI/CD pipeline and a key element of a continuous ATO process. Now, pulling back to what you heard this morning, you heard complementary approaches to source code analysis. You heard approaches for automated binary code analysis. And these techniques are also suited for program offices when they're integrating external code or they're integrating legacy modules for which the source code is also no longer available. This approach is also dual use for cyber operations because it's directly applicable to a binary analysis use case you often find in malware. What we're now going to be doing in the program is pivoting a little bit from the research primarily on analyzing code to looking at the dependencies you have when you construct those systems and the operational practices to manage those systems. This will also be followed by looking at evaluating Tradecraft and the operators that are running it. And so next up is going to be Dr. Will Claycomb hosting a panel for us on discussing resiliency in the supply chain. Over to you, Bill.
Thank you, Roman, and welcome everyone to this afternoon's panel on implementing cybersecurity in DoD supply chains. I'm Dr. Bill Claycomb, principal researcher here in the CERT division of the SEI, and I'll be your moderator. We've got 5 excellent panelists with us today to discuss this important and very challenging issue, and I'll introduce them shortly. Supply chain has really always been an important issue, whether we're talking about historical examples of armies running out of supplies at exactly the wrong time, or store toilet paper shelves being empty during the first couple months of COVID this year. And not to diminish the challenges of toilet paper or hand sanitizer supply chains, but shifting the challenge to technology supply chains, that is, the hardware and software components needed to assemble a working technical system, we're faced with perhaps an order of magnitude more components, and components of significant complexity, where it may be impossible, or at least infeasible, to examine every chip or every line of code to make sure that it's trustworthy. For DoD, the problem is further compounded by the significant risk that elements within the supply chain would intentionally introduce untrusted components, perhaps so they could then exploit those vulnerabilities against the DoD. So I hope you agree this is a challenging and very complicated problem to address. But fortunately, we have 5 experts with us today to share their thoughts and answer questions about implementing cybersecurity in DoD supply chains. So I'll briefly introduce the panelists. First panelist is Mr. Joe Bradley, the Director of the Air Force Cyber Resiliency Office for Weapon Systems, where he's responsible for changing the cyber culture and increasing the cyber resiliency posture of Air Force weapon systems. Previously, he served as the Director of Engineering at the Air Force's Nuclear Weapons Center, responsible for both the existing nuclear weapons inventory as well as the systems in development, including the ground-based strategic deterrent and long-range standoff weapon systems. Prior to that, Mr. Bradley served as Deputy Director of International Strategy for the Air Force, as well as the Director of Engineering for what is now known as the Digital Program Executive Office. Our next panelist is Dr. Carol Woody, Principal Researcher for the CERT Division at the SEI. Her research focuses on building capabilities and competencies for measuring, managing, and sustaining cybersecurity for highly complex network systems and systems of systems. She's co-authored a book called Cybersecurity Engineering, A Practical Approach for Systems and Software Assurance, published by Pearson Education as part of the SEI series in software engineering. And she led the effort to develop the CERT Cybersecurity Engineering and Software Assurance Professional Certificate. Dr. Ken Mai is our third panelist. Dr. Mai received his BS, MS, and PhD degrees in electrical engineering from Stanford University and is currently a principal system scientist in the electrical and computer engineering department here at CMU. His research interests are in high-performance circuit design, secure circuit design, radiation hardening by design, reconfigurable computing, and computer architecture. Our fourth panelist is Mr. Matt Bukovic, Technical Director for the Cyber Risk and Resilience Assurance Directorate here at CERT. Matt performs research on critical infrastructure protection and develops methods, tools, and techniques for evaluating capabilities and managing risk. This includes addressing the challenges of complex supply chains. He also teaches graduate-level cybersecurity policy courses for the CMU Hines College and serves as an instructor for a number of courses focused on organizational resilience and supply chain risk management for the CMU Hines School's CISO and CRO executive certificate programs. Matt has more than 20 years of managerial and technical experience in information technology, particularly information system security, process design, and audit in the banking and manufacturing sectors. Fifth, I'd like to introduce Dr. Mark Sherman, the Technical Director of Cybersecurity Foundations Directorate here at CERT. His teams focus on secure development processes from threats to testing and on the interplay between data science and cybersecurity. Mark has been with the SEI for 7 years, and before that, he held various technical leadership positions in Fortune 500 companies as well as startups. Finally, I'd like to give a call out to my good friend and my manager, Dan Costa, who is helping us today behind the scenes. Thank you, Dan. So let's get started. I've asked each panelist to give a few minutes of introductory remarks. And after that, we'll take questions from you, the audience, via the chat feature of this YouTube session. So please don't hesitate to submit those questions. We'll get to as many as we can in this hour-long session. Mr. Bradley is kicking things off for us. So I will hand it over to you, Joe, to get us started.
Well, thank you very much, and thank you for having me today. This is it's a timely topic. You know, there's an old saying that says, you know, but for the want of a nail, the woe is lost, right? And think of that now, not in terms of getting horses to the front, but think of it in terms of cybersecurity. How do I make sure that my supply chain is, number one, available to me, and number two, secure and resilient, so that when I actually pulse that supply chain, it's there to support my needs? You look at what's happened now. My job, just really quickly, is to make sure that the weapon systems that are provided to our warfighters are resilient and secure. And more importantly, the supply chains associated with those weapon systems have also got to be secure, so that we don't wind up introducing either defective parts or malicious logic that comes through the supply chain. Under the great power competition, we see the fusion of our military and commercial sectors. Adversaries are weaponizing commercial activities as a means of degrading the U.S. military capability. An example is Russia cornering the rare earth markets, China's practice of commercial exploitation, including pressuring companies to transfer technology to their partner companies, exploitation in networks of scientific, academic, and business contacts to steal technology, and the potential exploitation of the DoD commercial supply chain to introduce counterfeit parts. Why is that important to me? It's important to me because I need to make sure that as I pulse a circuit, it responds the exact same way as it was designed. It's important for me to understand what my networks look like. We have a thing called the Trusted Systems Network Program Office. There, we're actually looking at components that make up our systems. So it's a systemic identification and protection of components, and understanding that what we buy, what we procure, and what comes through the front door is exactly what we expect to go out the back door to our warfighter. So that's just a brief analysis of why the supply chain is very important to the Air Force and why it's important to me.
Thank you, Joe. Next is Carol Woody. Carol, the floor is yours.
Thank you. My research is currently focused on improving the ways that we engineer security into systems. Engineering and architecture are based on requirements, and too frequently we are seeing these as just lists of standards, practices, compliance mandates, anything you can think of, but they are totally disconnected from what's actually designed and how the architecture is actually built. The acquisition documents talk about information assurance, software assurance, supply chain risk management, anti-tamper. Each one of these is written as if they were isolated and have no consideration of the trade-offs that need to be made among all of these issues, as well as ensuring that the systems perform effectively and reliability. The result has been a lack of engineering rigor for the cybersecurity, which is needed to field systems that will continue to provide critical mission capabilities even in the midst of compromises. Addressing this gap is going to require us to think differently about the problem space. The engineer needs to determine the ways in which a system might fail and factor those into how they are designing the system to accommodate those risks, or figuring out how to avoid them, designing it to prevent these problems. Some of this thinking has been applied relative to safety, but what we're seeing is that safety really doesn't care that much about functionality, because a non-working system is very safe. Also, safety doesn't consider the level of increased vulnerabilities that are available to an attacker as we move into the software-reliant and highly interconnected systems of systems worlds. Add to this third-party software and reused components, and we have far too many gaps in our operational environment. What we have developed is a methodology that we call the Security Engineering Risk Analysis, SERA. And this is structured to guide engineers to develop and analyze what these security risks are, and to factor them in as part of their engineering and trade-off discussions. The approach is aimed at mission criticality and the potential impacts of these missions. We have piloted this in various contexts and have successfully improved the security requirements for acquisitions. We've identified security risks in operational systems that were then addressed with expanded operational controls in advance of a system compromise. And we've improved the ability of programs to identify mission critical assets to support their implementation of strong security practices. We're working right now on assembling a library of archetypes to facilitate engineers in thinking about the ways that their system can be compromised. This is not an area that they typically are strong in. SERA is best performed by a team that integrates designers, architects with security experts, because then you have the broad understanding of how systems can fail, along with those that understand the functionality and what needs to happen. We're seeing that investing the time early in a program to apply the engineering rigor that we need for cybersecurity can successfully improve the situation in operational risk. Thank you.
Terrific, Carol. Yeah, very interesting stuff, and very important topics as well. I'll then move on to Ken Mai. Ken, go ahead and take it away.
Thanks, Bill. So my work is really looking at the area of untrusted fabrication for integrated circuits, right? The concern here is the integrated circuit itself nowadays has billions of devices on it, has feature sizes in the single-digit nanometer regime. So verification of that is extremely difficult. And so if it being fabricated in an untrusted facility or by an untrusted, extremely problematic systems, right? The primary issue in the industry in general is that the center of mass for integrated circuit fabrication has been moving overseas, has been doing that for quite some time, primarily Asia, and they're very few, only the entire model for the way integrated circuits are built in industry has been changing, right? In the olden days, you had very vertically integrated companies where they did everything from the device design and fabrication through to the IC design, the architecture design, and the system design all in one company. Now, we've moved really to a fabless semiconductor model where you have companies that design integrated circuits, but they fabricate them with a third party, different company, again, primarily overseas. Now, the issue for the USG is that there are really three pathways to creating integrated circuits that we can trust and have security. So the first is essentially the most unpalatable one, which is the government buy, own, and operate a fab, right? Which from both a technical standpoint and a cost standpoint is quite prohibitive, right? For leading edge and all trusted, right? For example, IBM had a trusted fab program for a number of years. But there are a smaller number of US fabrication, I'm seeing in the chat that I may be losing the audio. Bill, should I turn off video? Would that help?
Yeah, Ken, we're having some issues with the video. Maybe try turning off the video and see if that helps clear things up.
All right, I'll turn off the video and see if that's better for that. But again, the next option outside of USG owning and operating a fab is that we can use domestic fabrication resources, but there are very few of those, right? For US owned and operated, you're looking at Intel and Micron. Additionally, Global Foundries has fabs in the US. And finally, TSMC is at least committed to potentially building fabs in the US, but hasn't done that yet. Now, the third option is to essentially do something clever, but still fab overseas, right? And there's been a lot of work in terms of doing logic locking and split fabrication, a number of different things that are possibilities for still creating a trusted integrated circuit, but fabbing at one of these third-party fabs, primarily in Asia. Now, the downside of this is that a lot of this work has yet to be integrated with commercial design flows. And so, I hate to say it, but there's, a certain amount of snake oil being peddled here, and that it really requires sort of a vertical integrated solution going from the architecture all the way down to the tools in order for us to have a solution that's palatable and that will generate the circuit that we need. So the last thing is that for USG needs, there are a number of different specialized fab requirements that often aren't pushed very hard in industry. An example of this is building rad-hard circuits for aerospace and space applications, which is an enormous industry as far as the third-party fab houses go. And so there's a question about how the US government can push their priorities while unfortunately now not being a large percentage of the overall integrated circuits being fabricated, which was not the case a few decades ago, but unfortunately now, right, US government needs aren't a large percentage of the circuits fabricated, so they don't have the leverage.
Okay, I think looks like we lost Ken. We'll hopefully be able to improve the connection quality before we get to the Q&A part of the session. But as you can see already, just in the first three panelists that have introduced themselves, we've got a wide range of expertise available to you today. So again, to the audience, please feel free to ask questions, even now, so we can get them queued up of these experts. So next, I'll turn it over to Matt Bukovic. Matt, It's all yours.
Thanks, Bill. It's a pleasure to be here this afternoon, and it's good to see we're demonstrating resilience, even in our panel, given the telecoms issues we're experiencing. So, Bill, when I was thinking about this session, and I'd like to posit to the audience that there's really two attributes that I'd like to focus on in my remarks, and certainly this has been at the center of the research we've done recently in supply chain risk management, and that is trustworthiness and prediction. So recently, my team, in conjunction with Johns Hopkins APL, produced the CMMC, the Cybersecurity Maturity Model Certification. So determining rigorous ways to measure and then drive behavior regarding the trustworthiness of DIB players. At the end of the day, we want to ensure that we're trusting only the right parties, keeping the wrong parties out, and understanding our dependencies. So I think that from my vantage point and from my research prerogative, I'm most interested in measurement. I'm most interested in this concept of trust and resilience based on trust. So trusting the right things, understanding your risk. I would also add that an underexplored facet of supply chain risk management, from my perspective, are services. And what I mean by that is not just wafers or software, but rather the storage and compute services that we're purchasing, right? So I think that one of the things we, and I think it was so succinctly put by Joe, which is we see this convergence of DoD and commercial enterprises and capabilities. As that grows, our problems or our challenges become more comparable. And chief among those, I think, is this consumption of services in a way that allows you to find parity with your security requirements when they were wholly your own. So I would suggest that maybe a little far afield, but maybe that's the point, Bill, of this panel. When I think about supply chain risk management and the DoD, I think we have to be equipping the stakeholders with a new skill set. So certainly everything we've discussed today in research review, all of the traditional engineering applies. But I'd argue that if we're going to place an increasing reliance on third parties, then understanding third-party risk management, understanding the fourth-party problem, understanding the distribution of risk and dependence and elongated supply chains, the tools and education and skills for those need to be imparted to the folks managing these situations. So I'll stop there so that we can ensure we have a lively discussion. But I think, as you said, Bill, we have a number of disparate but related topics emerging here, and all of them should be front of mind for anyone interested in supply chain risk management.
Terrific, Matt. Thank you. I heard a few things that hopefully will come up again during the discussion. The notion of the services that we consume, that is continuing to be a growing challenge as we tend to shift towards that model. But the other word that I heard was prediction, and I'd really like to explore that a little bit more. But hopefully we'll have some questions about that. Our fifth panelist is Mark Sherman. So Mark, I'll go ahead and turn things over to you for your opening remarks.
Thanks. Good afternoon, everyone. There's an urban legend circulating around the SEI. I say that because I've never been able to track down by name who said it, but the legend is that an Air Force general came to visit once and commented, "I used to win wars by bending metal better than anyone else. Now I'm better than the adversaries by having better software." And as a result, we tend to think of supply chain as largely hardware kind of issue, pieces, components, boxes, but software is becoming really the guts and the intelligence in these systems. And if you heard the panel yesterday with Dr. Cummings, she made a remark that I had never heard before, I found quite interesting. She commented that when planes launch off of aircraft carriers now, the pilots have to hold their hands up to verify that it's the computer that's taking off from the aircraft carrier, not the pilot, because it's so much better at doing it than the human in today's systems. And so it's very important that we understand the supply chain around software. At best today, it's a part number in a larger set of components. So we have power supplies and cases and whatever, and one number that says software, or even worse, it's embedded in a piece of a box of something else, and you don't even see it, and just the box number that has it. Because software is so malleable, because it is so vulnerable in general, we really need to be able to track the various pieces of software that are in a system at a granular enough level that when something goes wrong, we can understand what that piece was that went wrong. And as importantly, because software is vastly reused, to understand where else that problem may arise in other systems that we have that are built out of common components. Historically, the DoD has focused on just immediate suppliers, not the entire supply chain. And to understand really what's going on, you have to understand all the components down. It's not simply that defense contractor provided you this particular piece of software, but inside of it has other pieces of software all the way down. So you have a quite a long potential both fan out in depth of what the software chain looks like. Just as a rough feeling for those who haven't actually looked at the numbers. A typical fan out, that is how many different kinds of things of peak components you might have, can be in the hundreds. The depth can go into the tens. You have thousands and thousands of software components potentially in one of these kinds of systems. Something that also the software supply folks, as they're looking to provide this kind of capability within the software supply chain for the Department of Defense, is to take a little bit of sort of history that came out of other supply chains. And I will tend to look at, for example, the food industry as a good example of it. First, we use the word supply chain, even though many of the times that's a shorthand for supplier and not really a chain. But in practice, it's not even technically a pure supply chain. It's what's more commonly called a value chain. That's because as the component moves from place to place to place, whoever's touching it adds some value along the way. So think in terms of, again, the food industry. Your bagged salad, it started with lettuce, it goes to some distribution center, it eventually gets taken apart, it gets washed, it gets rebagged, it gets repalleted, it gets taken apart, and when it hits the distribution center and the grocery store, each of those processing stages, each of those processing stages offers an opportunity, frankly, for something to go wrong. So it's not so much to know, although you do need to know that lettuce came from that particular farm and they had some particular outbreak, but it could be that something happened along the way in the processing of that lettuce. So same thing in software. It may be that when it came off the developer's original desk, it was pristine, but by the time it came to you, the processing that happened along the way introduced errors, and therefore or vulnerabilities. So you need to understand the entire value chain, not simply the supply chain of how a component went from piece to piece. A second lesson that you can take from the food industry is what I would call the invariant. And the best examples of this, for example, are called the cold chain in food and pharmacy, or if you're working with law enforcement, the custody chain. But the idea is there's something that you can say about the component that doesn't change as it moves from place to place to place. So if it has some sort of security validation associated with it, that security invariant has to be maintained as it gets added or subtracted to other larger components that eventually gets into the plane or ship or whatever it is that you're building. The last one is what I call the tool issue. And again, looking at the food industry as an example, you see these warnings on your candy bars saying, this was processed on a machine that also processes nuts. That's a way of saying that even though the chocolate may not hurt you, the fact that it was produced on a machine may still have implications to you. As it turns out, the tool chain that's used to build software is an increasingly vulnerable and exploited method for attacking software. There are various examples in where tools that are used to compile it or otherwise process it have introduced the errors, even though what the programmer wrote was fine, the compiler was fine, but the other kinds of tools that touched it along the way added vulnerabilities. And so all of these things require us to be able to track and understand what components we have at a granular enough level to fix things whenever we learn them, either because they're errors or vulnerabilities, as well as the tools used to build them, because that may be the source of any vulnerability that was introduced. So we've got, with the shift of the world mindset to having software basically replacing hardware, we need to start thinking the software at the same kind of granular replaceable level that we think in terms of the hardware components and the chips.
Terrific, Mark. Thanks. I wanted to go ahead and just come right back to you with a question along the lines of the supply chain, the chain of custody analogy that you made. A term that I've heard recently is the software bill of materials, the SBOM. Is that what? Can you explain that a little bit more? And is that essentially what you're describing as this chain of custody, or is that something different?
So the software bill of materials, or SBOM, as the people working on the standard tend to abbreviate it, is a way that you can start to categorize the pieces that are in your software package so that you can start asking those same kind of questions that we asked. You know, do I have a component that's been attacked or made vulnerable in some way, or have we found a problem with this particular component? So attaching a software bill of materials to the final thing that you get is certainly a start. How you implement that in the entire chain becomes problematic. For example, you may have vendors who feel that they have competitive distinctions. They don't want to tell you what's in those pieces because they think that's their magic sauce. And by revealing that, they'll be competitive. They'll have a competitive disadvantage. And frankly, I've actually experienced this in my own life. One of the startups I was with built OEM software that went into other packages. And frankly, half of our customers wanted to tout that we were contained in them because they thought that was a way to show they were new and different and improved. And the other half didn't want it there because they thought it would take away their brand value, the thing that it was contained in. And they wanted to say that they were the brand value, not the stuff that they licensed from us to put in. So that's a recurring commercial tension that doesn't have a very easy answer. There's also adversarial disclosure. It turns out that much of software that's composed and distributed, frankly, is out of date and has known vulnerabilities in it. The CVE is filled with information about vulnerabilities of existing packages. And if you reveal in detail what's inside your package, an adversary can basically look at that same bill of materials and say, I know exactly how to attack that. And in fact, we discovered that at one of the energy labs where they bought some commercial software. When they looked inside, they found it had a variety of things that if the people knew what was in that commercial software, they would also know immediately how to attack it. Sometimes they don't even know what the composition is. If you have someone who wants to do this, you can not always rely on it. Again, I worked for another company and where they wanted to be very meticulous about understanding what pieces were in there. Frankly, they were worried about legal liabilities more than vulnerabilities, but they wanted to make sure that nothing went out that they didn't know about. And so in fact, they made all the developers sign affidavits before a software product went out saying, I promise that I did this, this, and this, and I didn't go out on the net and grab things or what have you. I was amused to learn later that I talked with one of these companies that does software composition analysis. It's a whole new chain of tools that have come out. And I commented, I worked for this company, and in fact, I was a product manager for one of these products. And I said, and it was part of a discussion of, is this software clean or not? That is, this what we know is free of vulnerabilities. And I said, at this company, we never put in stuff that wasn't checked. And he said, let me tell you a secret. We've run our tools on that piece of software, and that's not true. That's not actually what actually gets put out in the market. It also can hinder some flexibility. And this is somewhat connected with the granularity issue. Let's say, for simplicity, you're talking about you include a Linux distribution in your software package. Linux is in almost all your IoT devices that you look at. But it's not the entire Linux distribution. That Linux distribution has thousands of components. When you take out all of those components, what goes in the bill of materials? Is it just the things that you left in? What happens if you want to put one of them back in later? And finally, you're worried about legal protection. Again, in the case of that one company I was referring to, if it became disclosed that they actually included something that violated a patent of another company, something they tried to avoid, but again, if you don't really know what's in there, then it opens up for legal liability. It's frankly, obscurity is security for them in that respect. If you don't know what's in there, you can't be sued for having it in it. So there's a lot of issues involved to make this a practical process. Standards are starting in where they're going to layer the kinds of details that provided in the bill of materials, but we'll have to see how it rolls out in practice.
Terrific, Mark. Thanks. That was a really detailed answer. I appreciate it. I want to shift over to Mr. Bradley for a minute and sort of present a more open-ended question. So Joe, if you were king for a day, say, what would you do to enhance the cybersecurity of DoD's supply chain?
Thank you. Great question. And I worry about that a lot. I wonder sometimes, you know, if I could make the rules, what would I do? I would tell you that I would get away from commercial off-the-shelf technologies. We fell in love with that because it was a great cost savings and it supposedly increased the speed at which we could field systems. We're averaging about 7 years to get a system from concept to field, and that's just way too long. I would go more towards, you know, back when I was going to school, you had a TTL logic design book, right? And you could build any chip you wanted as long as it was in that TTL logic book. So what I'd like to do is I'd like to pre-screen the parts and the software, you know, whitelisting of code, and just say to folks, hey, you know, you need to build this single board computer or this unique device using these pre-approved parts. Okay, so if I go to the store and I buy a box of Legos, I don't see any Tinker Toys in them. I see Legos. They fit together, they work together. I'd like to do that, and I'd like to see that in the Air Force acquisition process, where we use the Trusted Systems Network lab down in San Antonio, but we use it after the fact. After we've spent a year or so into the design phase, then we say, hey, let's make sure these components are what we expect. How do I bring that further to the left so that we can do that? If I were king for the day, I'd mandate that would be it, and we'd only build from the components and parts that were through that lab and approved.
Okay, so I guess I'd like to think about for a minute something you said right at the beginning of your comments about shifting away from COT software and shift sort of back to Matt's opening statement about the increased reliance on services. You know, that we're relying more on the hardware and software that's provided by third parties. So Matt, I mean, do you think that that shifting away from sort of reliance on COTS is congruent with an increased reliability on a more service-based approach?
Well, I think the answer might be that we should be asking more of those that produce those COTS products, right? So with Joe's observations regarding understanding what's in the box, right? So I think Mark did a great job of explaining some of the traceability problems that we have. The need for a software bill of materials is one. And if you expand that concept broadly, we need to have a traceability element to all of this, be it a component, of course, or software, increasingly services. How do you know the right activities were conducted related to the service you've purchased, right? So Bill, do I think the world's going to go back to buying bespoke hardware and software? I don't. I think that's a hard sell. Are there specific strategic and sensitive areas where that makes a lot of sense? I believe so, and I'd love to hear more from Joe and others about that. But I think that being in this converged world of IT software, or sorry, of IT services, software and hardware is probably here to stay. In fact, if you look at things like the rise of a network function virtualization, where very elaborate and dedicated engineering is required to allow for network connectivity, being replaced by scads of consumer grade Linux boxes pretending to be routers, I think we're actually headed in that direction. And I think that we sort of can't fight the future, but we can ask more of those that are shaping the future. So I think that it's really us being smart consumers while recognizing that we're probably not going to have the same direct degree of control in the software, hardware, and services that we're purchasing and acquiring now than we did in the past. It just, the world is increasingly requiring us to put faith and ultimately hand the reins to a third party.
Carol, do you have any thoughts on that?
Yes, I'd like to add a little bit to that. We tend to stovepipe the way we think about a system, what we decide we want to have, and then go off and assemble all of these parts, put them together, and then we're surprised we don't get what we thought we wanted in the first place. And I see that as a huge disconnect because you've got decisions being made at different points in time that are not integrated together. If you're engineering in cybersecurity, then you need to be looking at it from the perspective of what code am I getting? Where is it coming from? Third parties? Does that meet what I need to have? Part of that should be part of your selection criteria. Not just, oh, I'm going to use all of these pieces because I happen to already have them around, even though they don't quite do what I want to do, and I have to Rube Goldberg jury rig them together, and God knows what else I've put in between. And I think this holistic approach, Matt, just continuing on what you're saying, but adding more to the group in terms of tying it back to what you said you needed, what the stakeholders think they want, and putting rigor into all of those pieces with solid trade-off choices. because you can't have everything. You know you're going to have limitations. And by the way, you've got a cost and schedule you have to live within. So all of those pieces need to tie together. But I think we need more of the right minds into the problem set at each point in time. We don't need somebody in acquisition going off and making some choices that are separate from what we know we can do and how the pieces need to work together operationally. My 2 cents.
No, that's terrific. And I guess, we've been talking a little bit about software from software perspective. Maybe we can shift over to more of the hardware and circuit design and get Ken's thoughts on the issue of COTS versus sort of bespoke products.
I'm sure. Hopefully my audio and video hold up. Oh, maybe not. So I'm getting the notification that I have unstable internet. So I'm going to clip off my video, unfortunately. All right, so I think there's an interesting question here about COTS versus bespoke parts. I mean, this came up a number of years ago when there was a push in DoD circles to move towards FPGAs and programmable solutions versus ASICs, right? And I think, and so we hear a lot of people talk about, for example, in the F-35, the enormous number of FPGAs in those systems. Now, the challenge is that I think there was a notice that, well, if you go to FPGAs, you're losing order of magnitude or more in performance, energy efficiency, even though the overall cost is lower and the time to field the system. But so this is really looking at tools and generators. So we're not looking at handcrafting every piece anymore. And also to, I believe Pierre's point, third-party IP blocks and how we accrete those together. Now, there's one interesting piece of technology that's recently come. That's smaller integrated circuits on essentially a carrier or interposer, so they look like they're on one chip. For those of you that have been around for a while, this is similar to the old style of multi-chip modules and MCMs. So there's been some government investment in, for example, an interposer fab in Florida called Bridge. And so I think that's a technology where, as Joe pointed out, you could bring together a number of pre-verified parts onto a bespoke design and get a little bit of the best of both worlds, right? You're not costing quite as much as a pure large custom ASIC. You've pre-verified the components, but you can still field the part relatively quickly and get good performance, good energy efficiency.
Thanks, Ken. Really appreciate it. I think we made it through with just some minor issues on the audio, so good deal. Thank you. I want to sort of shift to questions about prioritizing needs for DoD. If we think about what are the most pressing issues, what is the most critical vulnerabilities or the biggest risk to DoD supply chain today? What would those be? What does DoD need to be doing today to address cybersecurity in the supply chain? And I guess, Matt, I'll go ahead and ask you to kick off the response to that question.
Sure, Bill. Maybe I think I might start my answer in a place different than my colleagues in the panel. I'm not going to give you a technology or a threat actor as an answer. I'm going to say the number one threat, the DoD supply chain or cyber supply chain, is complexity, right? Which is understanding the universe, the broader expanse of things we need to know to effectively make risk decisions in the supply chain. So I think if the supply chain is deeper and it's more elongated and it's more opaque in ways than it ever has been. So I would argue that those facets of the challenge are the most enduring. The technology stack is going to change over time, right? If we were doing this panel 10 years from now, who knows the specific technology we might be discussing. But I believe these questions and challenges of complexity and visibility will be with us for a very long time. And I would then posit that we should concentrate at least some effort on addressing those challenges in addition to the technical challenges.
Terrific. Does anybody else want to jump in on that one? Mark?
Well, Joe, if you want to, I'm happy to let you go next.
Yeah, thanks. Just real quick, I'd like to add on that. You know, the other challenge we're going to have is provenance, right? Where do things come from? Where were they built? Where are they used on? What are the other systems? And then if I know what the systems that I have and how they function, and I know that somebody else has them, can I then exploit that, you know, in the supply chain? Can I then have a look, feel, similar software, similar hardware into the supply chain? So it's just understanding what's the pedigree look like of the components. Or
okay, Mark.
Sure. So although I'll remain technical, despite what Matt was suggesting, but I also take a different viewpoint here. I think the biggest issue that we've tried to address when working with our DoD customers is not spending a lot more effort on hardening the supply chain per se, much as we would like to. We've all gone through the various challenges in trying to do that. But starting with the belief, maybe I'm in the minority here, that both COTS and open source are going to be more important and increasingly installed into DoD systems. It's managing the results of having a bad component in your system. How do you build these things so they are resilient and they can recover and they can even monitor what's going on? So when we talk about designs of the next generation of systems with our customers, we're talking about how they introduce diversity, heterogeneity, redundancy, and monitoring as a way to keep track of what's going on. And when something goes wrong, and it doesn't take a lot of imagination to think of some autonomous system or some system that's not readily accessible, that it has to self-detect it, has to be able to somehow partition off the bad piece, ideally maybe even somehow repair or at least mitigate whatever the problem was to get back to the functionality. Understanding that you're not going to be able to manage the risk, you're not going to have full provenance and pedigree of what you've got. So instead, how do you manage these untrustworthy components in order to build a system?
Carol, do you want to add something?
I'd like to add another consideration here, and that is the push from the program offices we've seen, because they are financially constrained, is always to the cheapest solution. And we are seeing continually the lack of consideration of how the security of those pieces and how the functionality is managed and maintained is not part of that choice. And so broadening the aperture in terms of the considerations around the selections in the supply chain, I think is going to be critical in terms of moving forward. We're also seeing a focus on shared resources that will be used broadly across multiple programs. But we're not seeing consideration of the differences in the risk positions of the multiple programs that are using them, and effectively figuring out the inherited risks so that you're addressing the right security concerns within a program itself is going to become an increasing challenge. So supply chain offers a lot of opportunities, but we're not, I think, effectively considering the risks that are coming along with it in terms of systems design.
Yeah, I think you're right there, Carol. I agree. We have a question from the audience, from Tom, who asks, can the panel address how the rise of hardware and software co-evolution complicates these issues, especially where vulnerabilities and risks arise as the emergent behavior of these complex systems? So Matt, do you want to take a stab at that? Yeah, I think you're on mute.
My apologies, Bill, I was on mute. So great question. I think to kind of, when I'm framing this for myself, I'm thinking you have this population of vulnerabilities and complexities related to hardware and software, right? And those are challenging enough on their own. And then as you watch this interplay between the two, you're left with a host of new considerations, right? So I think that maybe at the heart of that question is an understanding that we should all have, that the hardware and software technologies will grow by fits and starts. They will be in different stages of evolution at any point in that continuum. And that may produce results that are very difficult to manage. I think Mark was spot on when he said that the goal needs to be ensuring that we can return from some disrupted or degraded state
in our software and hardware systems in the supply chain. So yeah, I guess as sort of an answer overall, I think this is an area where convergence might, in my opinion, I'm going to nominate for maybe theme of the panel. If we're looking at these as different engineering disciplines, this is certainly the spot on the Venn diagram where we have to cross, right? The hardware engineers and the software engineers. Also, we know that those lines are blurring, right? That devices now can be kind of both at the same time or neither, right? Depending on mode and use. So I think that the question identifies an emerging, in my opinion, potential blind spot, and we need to ensure that collectively we understand how the interplay between these things is reshaping our understanding of it.
Terrific. Anyone else want to add anything on that?
So again, I'll offer a slightly different spin. As you might have guessed from my previous comments, would argue there's really very little, if any, distinction between hardware and software. They're just particular ways that the rules and algorithms get packaged up and delivered. Saying that somehow FPGAs or creative manufacturing or just raw C code are somehow inherently different. I think this is the point. I think they're actually quite the same. And we don't even think twice now about the fact that we're programming our printers to print things, as opposed to in the past where we just had images that got copied automatically. And so I don't think so much the hardware-software interaction. You could ask that same question about any number of components that have to be co-developed. The fact that one's in silicon or not, I think, is an artifact, not necessarily the core issue. What I think a more challenging issue is what I'd call the change in operational environment. When we build these systems, we usually make assumptions about how they're going to be operated. A very crude example is I don't have to worry about securing this particular system because I've got fences and guards sitting around it, and therefore that's enough. All of a sudden, when you're in a situation that's not true, then that has a problem. It's a couple of examples that people are familiar with. The furnaces in Germany that got destroyed because the SCADA system got compromised. Now, I'm sure the person who built the SCADA system never had any thought that somehow someone was going to get into their SCADA system and they had to protect against sending bad commands out to the furnaces. But you can see the history. They did the SCADA system and marketing said, well, let's connect this up to the ERP system so we have a view of what's going on. And then the salesman said, let's connect it to the CRM system so that I can figure out what I can sell or not, what's being produced or not. And then someone said, oh, let's make customers see what the status of their order is. They put a web interface on it. Now, all of a sudden, the attacker could get through the CRM system to the ERP system to the SCADA system and destroy the furnace. Same kind of thing with the brakes on the Jeep. I'm sure the guy who programmed the brake software had no concept that someone was going to come through the entertainment system and be able to control the brakes remotely. So he had a zone of trust, and that got violated. And as we build different components that are fitting together, we make assumptions about how those components will interact. And when they get put in a different operational environment, those assumptions get violated, and that introduces problems.
So Mark, I'd like to sort of pivot on that idea that sometimes it's the components that we don't expect that introduce the vulnerabilities. And so when we think about supply chain security, introducing more security into the supply chain, can we say that some systems maybe are more important to consider in terms of supply chain than other systems? And so as sort of an extreme, just to illustrate the question, we have IoT devices on one end, the smart devices and things that sort of have one little function versus maybe the back end servers. And so, should we say that, if we want to focus our supply chain security efforts, that it would be more important to focus them on the big heavy duty back end stuff or the little ones, because there's a whole lot more of them. So I was going to get Carol's thoughts on that. Carol?
One of the areas we're seeing that's becoming critical is not so much to focus on specific pieces of hardware or software, but to really understand what your missions are dependent on. Your mission threads, the scenarios of what it's going to take to get your operations done. Because if some small hardware piece that's not critical to your mission gets compromised and there's not a direct connection that's going to be a worry for you in terms of completing the mission, then that's probably of less concern. But what we're seeing is that very few of the programs are actually really thinking through all these parts and pieces I'm assembling. What is it I'm really depending on to have my mission complete? And which ones of these odd pieces that I'm concerned about can become attack vectors? So if we just focus on critical assets in the middle and put extra protections around those, if we haven't also thought about how we've left open potential vectors to come in and attack, which could be from IoT devices, they could be from servers that you're connected to that maybe you don't even control, or other pieces that you haven't really looked at because you haven't really articulated what your mission is dependent on. And it may be other related systems that some other program controls. It's all of these integrations that are adding to the complexity that are actually making it more difficult for us to determine where we do need to focus. Because in reality, you can't fix everything. And I think we've already mentioned that you have to recognize, resist, and recover. But you have to plan that into how you're designing your systems as well. And which pieces do you recover? And what do you keep as the most important up and running? It's probably the pieces that you haven't really thought about that are going to be the real challenge to you. And that's where we're talking about engineering rigor fitting into this. Really not just designing all of these pieces with all of this possible functionality that you might be able to do, but what are you really relying on, and making sure that that's really hardened to the extent that you can in terms of monitoring and managing the pieces and parts. And some of those might be these little IoT devices because they're your key communication mechanisms from the employee that's now working at home to the main system that you're trying to run in the offices and keep your everyday operations up and running. So we have to think in terms of what is it we're really relying on, and how do we really harden those to the greatest extent possible.
Mark, did you have some comments on that?
Sure, I'd like to follow on a key comment that Carol just made. It's the importance of the system, not the technology. It's not so much IoT versus whether servers. It's my pacemaker versus my Space Invaders game. I really care about my pacemaker not being attacked. I'm less worried about my Space Invader game being attacked. And that's really where I have my focus. Someone named Sandy Clark did an analysis of where do bad guys go after, and if you might, as you might imagine, the results are not surprising. They follow the money, and so things that are of high value that they can extract value from, that's where they want to go, and that's where you put your efforts. There was a recent interview of a Russian syndicate that was published. I don't know why they would give such an interview, but they did, and the person there stated, you know, we go after things like hospitals and banks because they have the money to give us. Sure, I can hack an Android phone, but what do I get for all of that effort? It's a lot of effort, no return on investment. I'm going to go where the money is. And so too, that's where I would spend, efforts in order to secure things, whether it's supply chain or otherwise.
That makes a lot of sense, Mark. And I'd like to keep going on that because it's a really interesting issue. But unfortunately, our hour is almost up, and I did want to go ahead and give each panelist a minute to sort of present any final thoughts before we end the session. So Mark, since you went last during the opening remarks, why don't you go ahead and go first here for the closing.
Sure. Thanks, Bill, and thanks everybody. I think it's been an interesting hour or so. My closing comment would be that the topics that we've been talking about here, I've had the experience of introducing to various DoD programs, and in my experience, I see light bulbs going off. The recognition of what these issues are is now being taken to heart, and it's now a matter of trying to implement those in appropriate policy, language, and processes that they have to work through. But at least the need is now more clearly understood.
Terrific. Thanks, Mark. Matt, over to you.
Yeah, Bill, thanks. I'd like to first thank my fellow panelists. I think it's a really great discussion. We could probably have another 3 hours of it if the schedule permitted. So focus on the critical few, right? That's the main takeaway that I would offer, which is we know the supply chain is vast. It's even malleable in meaning, as Mark pointed out, value chain, supply chain. What should you focus on? Well, things that are life critical, safety critical, of course, but beyond that, what does the list look like? So I would say, kind of in closing, if we apply the things we know work in risk management in other domains and disciplines to these challenges, it will show the way for us.
Terrific. Thank you, Matt. Ken, over to you for closing comments.
I'm not going to risk my video this time. So I just wanted to make a point about sort of where the discussion's been going and this focus on, well, which systems do we focus on? I think one of the things to be concerned about, from my perspective, is if I think about the circuit board itself, while yes, there are 10, 100, multi-$1,000 parts on there, there are also typically thousands of 1-cent resistors and capacitors and so on. And those are vectors for attack in counterfeiting and robustness problems just as easily as the $1,000 FPGA is. And so I think there, sometimes there's a focus on the expensive parts, whereas the overall system is built up of a few expensive parts and thousands of really cheap parts. And the problem is that those 1-cent resistors suddenly become $50 resistors if you apply supply chain tracking and everything else to them. And that's just something from an economic standpoint we need to be concerned about.
Yeah, I think, again, there's a whole huge discussion that we could have had around the economics involved with all this. And so you bring up some very interesting points that I wish we could dive in. I wish we had another hour, but thank you for your comments. Carol, we'll turn it over to you.
I would summarize by saying don't be daunted by the complexity. There is a vast number of ways and things that can happen. But if you start with your operational side of how do you want the pieces to actually work together and what's your most critical and work back from there, you can create a very good picture of where you need to place your priorities and the ways in which you need to think about the pieces to ensure that the operational environment you want keeps running the way you need to have it run. And you also need to design in ways to keep it resilient. We see that as an area that is not as strongly emphasized in terms of the system's design. There's a push for functionality and less of consideration of mission resilience. And if you focus on those two areas, I think you can make a good dent in critical areas with supply chain as well as just overall cybersecurity.
Yeah, I think designed in security is probably a common theme throughout several of the sessions during the research review here. It's a really important topic to consider and something that people need to be focusing on more. Joe, you are you're the last one. Go ahead and bring us home.
Oh, thanks. I'm probably all that's standing between the audience and a break right now, but thank you very much for having me. This panel has been fantastic. Some amazing minds, amazing thoughts, and I just feel honored to be among the people here. I kind of want to leverage a little bit of what Ken said. The item that we talk about a lot is your biggest risks are the items beneath contempt. Those 1-cent resistors, those things that you just say, oh, don't worry about it. They're not going to cause me a cyber issue. Those are the ones that are going to bite you at the end. And kind of, everybody's talked a lot about supply chain security, and it does start with component design. You have got to start your initial system design thinking about how am I going to keep this secure in the supply chain. I'm actually dealing with an issue right now where they didn't establish a supply chain, but they fielded a system, and I'm struggling with that. The thing we've got to realize is we're never going to eliminate risk. We really have to prioritize those essential functions, and we have to understand, well, what can we do? And what can we live with, and how can we live with them in a contested and degraded environment, and utilize all the tactics, techniques, and procedures available to us to get through. So thanks for having us. This has been great.
Terrific. Thanks, Joe. And thanks to each of our panelists for sharing your time and your expertise with us today. Thanks to Dan Costa also for helping out behind the scenes. And of course, thank you to you, our audience, for joining us today. So have a good afternoon, everybody. Take care.
Thank you.
Science fiction has long dangled cool visions of technology in front of us. And now, while over the years we've got some things down handily, like televideo phones and, say, leaving the planet, plenty of that future is still ahead of us. Artificial intelligence, specifically, promises to propel us on our way to some of those visions. Are we getting any traction with AI in the cyber domain? I wonder just how much sci-fi is involved with it. Will it be easy, like, say, flying cars? Or perhaps more difficult, like teleportation? Whichever the case, the newness of AI causes justified concerns about rushing it. So for the near term, we expect AI to stay on a leash. Recently, we read about an Air Force-sponsored AI soundly defeating a human adversary in air combat simulations. And interestingly, the Air Force is mainly talking about how AI can complement a human pilot. Likewise, the Army AI Task Force highlights the augmented side of their future AI spectrum, where processes bolster a warfighter's capabilities. Hopefully you caught my colleague Carol Smith's talk yesterday on the subject of AI ethics and understand why people want to be careful about rolling out new intelligent processes. All this means that human operators will leverage an AI technology as a subordinate, if not as a peer, in new teaming constructs. Can we envision that sci-fi future where cyber operators have the aid of processes that are both aware of the mission and have ample experience to act, or at least recommend action? Well, we have a lot of questions to ask and answer in order to make that happen. Where in cyber operations will AI be useful? Are there cyber tasks as straightforward as a dogfight, acquire, maneuver, and stop a foe? Certainly anomaly detection has been around a long time. Can it be made better with access to a broader scope of data? More specifically, can automatic correlation of disparate data sets find patterns and draw conclusions that significantly accelerate cyber domain decision making? And can we even generalize cyber operation tasks sufficiently? Though we're still working to frame these questions, we at the SEI are excited about teaming AI entities with cyber operators. In this talk, I hope to both convey a direction to travel and to articulate the foundation from which we're setting out. Now, the SEI is particularly well suited for this endeavor with its collaboration of machine learning expertise and cyber operations exercise experience. People on these teams have significant background and experience to drive this exploration forward. One such team focuses on cyber workforce development, led by Technical Director Chris May. While in the past that term had a connotation of training, at the SEI it means cutting-edge applications in the cyber modeling, simulation, and exercise domain. Several years ago, I was here reporting on our success with US Cyber Command's Cyber Flag exercise and how it really raised the bar for big force-wide exercises. Building off of our work to improve and scale hands-on cyber exercises, we transitioned a platform that published the state-of-the-art forward for the DoD. And we've continued that momentum by improving our tooling and applications to make even more realistic environments. That evolution has produced artifacts that can be leveraged for data set generation and AI test beds. The SEI has also cultivated relationships with stakeholders interested in the advancement of their cyber workforce. We appreciate the collaboration of our partners. Access to and feedback from their cyber operator audience keeps us on track and relevant to their vision of what the force needs for mission readiness. If human-machine teaming is to be realized, significant applied research is going to need to be conducted. This research includes machine learning algorithms, to be sure, but it must initially understand what operators need AI to do as part of that organic-synthetic partnership. So with that combination of internal teams and external partners, we're setting out to produce formalized data sets. Now, cyber exercises can be great data generation events. They produce a good ratio of normal and abnormal activity, and often with anonymous or clean artifacts, logs and captures that can be shared readily without running into a lot of policy roadblocks. And since an exercise is a somewhat controlled event, they offer some deterministic events. That's one advantage over pulling a set of, say, live real-world data. So exercise-generated data sets will be helpful to people asking those sorts of cyber AI kind of questions. Following this talk is an overview of the President's Cup Cybersecurity competition by my colleague Matt Carr. A data set resulting from such an event as that could be a rich trove showing how a wide variety of humans tackle complex cyber tasks. Participants in that competition hail from many government departments, the bulk of which are from DoD, and have many variety of backgrounds. Some folks are just starting out in their cyber career, and some who can really be considered elite. The challenges given them are compiled from the full spectrum of cyber tasks. In fact, those challenges are mapped to tasks and roles defined by NIST in the NICE Cyber Workforce Framework that they publish. Now, with these types of events, we have a real opportunity to develop models of cyber operators that formalize the state spaces of the domain. And defining those state spaces is going to be necessary to transform a heap of exercise data down into efficient data sets. What would that look like technically? Years ago, and perhaps ahead of its time, we explored the idea of automated cyber evaluation. The goal was to have a process watch an operator's screen and grade the execution of certain tasks. It was used by computer vision to look for solution cues that were designated by subject matter experts ahead of time. The competition challenge is a great variation on that theme because the challenges have clearly defined and graded endpoints, and we can capture how a variety of humans behave in that world and separate out the actors as well as normalize all of the actions. Then we can take all that data, the approach and methods of all the different participants, and feed that as a learning algorithm to a learning algorithm as training data. With that next step vision in mind, allow me to describe some of the tooling that can serve as a foundation to build on. Standing up infrastructure and configuring environments for this kind of data generation is not trivial. As production networks and services are complex, realistic models of them are as well. Add to that, they're generally ephemeral, so it isn't usually desirable to sink an inordinate time investment into getting them up and running. I mentioned CyberFlag earlier. When we were first selected for that effort, it was because we had creative and technical minds with good processes and applications. But it still took time, was troublesome to find errors, and truthfully required a lot of system-specific expertise. Since then, we've endeavored to reduce all three of those problems. And through that experience, we have promoted an infrastructure as code, as well as a DevOps approach to efficiently instantiating our simulation game spaces. Not only does this enhance the repeatability, improve the change management, and allow for easier transition but it also abstracts the more mundane tasks of setting up the hardware and configuring the applications. This is a topic for another day, but our infrastructure as code applications are known as Crucible around here, if you want to follow up. But this approach to infrastructure allows scenario developers to focus on the creative aspects of delivering an engaging and realistic scenario. Now, toward that end, we're developing several modeling and simulation tools to achieve the goal of engaging and realistic. Now, my contention is that these data sets need to actually surpass the realism of live data. As I alluded to earlier, the environment needs to feel totally real, but it often benefits from some time compression and some anonymized resources, as well as those deterministic events. The effort to balance this leads us down the track of actually using AI processes to generate training data in order to train other AI models, which could be really, really cool down the road. An application suite we have named Ghosts provides life to a scenario by managing NPCs, or the non-player characters. These characters fill user roles and they generate activity so that a network has all kinds of normal and abnormal packets flying around, and so that logs and sensors have data to collect. We have a sophisticated NPC generation process. It really draws from many public sources to create these user profiles that could be real, but aren't. They're fictional. It populates this profile with all kinds of detail to include a credit card, an avatar picture, and even a personality that's generally expressed as preferences. Then in the scenario, the character generally acts in accordance with that personality. And the demographics are generated sensibly as well. If the scenario, say, involves military units, then we spawn NPCs with reasonable ranks, roles, as well as geographic attributes. Their addresses will be near the base at which they're assigned. And along with another tool, the Cyber Decision Analysis Simulator, CDAS, we can generate a scenario and a geopolitical context that merges real-world current events along with a fictional storyline. This all leaves us with a rich opportunity to inject AI processes into our exercise scenarios for added realism and ease of constructing this game space world. I'm imagining this: pushing a button and having a high fidelity internet spin up. It's instrumented for data capture with users that build social networks over time and who collaborate actively to accomplish their objectives. Oh, and then we can let some humans in to play along with them. We're headed toward that future. Now, the work we've done with infrastructure efficiency and scenario realism isn't only applicable to dataset generation. It readily supports this concept of test beds as well. Realistic test beds are going to serve as the proving grounds for future breakthroughs in cyber AI. So it's feasible to generate a variety of data sets for learning and teaching a process, and then putting that process into a new, unseen before environment in order to test it out. So some of that high fidelity internet I mentioned comes from our gray box appliance, which is an internet in a box. It's called gray box because it projects the gray space in a scenario, usually represented as the cloud on network diagrams, or neutral networks not necessarily owned by the red team or the blue team. Now that projection in gray box is a robust representation of the internet backbone, with nodes spaced geographically around the world, and even with appropriate latencies in between them. And so it serves like top-level DNS, it serves web applications, it serves mail. The reason I wanted to call it out here is because we're starting to use this existing work as a test bed for zero trust concepts and applications. And that's also a topic for another essay. But I wanted to suggest with that the potential of using mod, sim, and exercise capabilities, not only in terms of AI, ML, data set generation, but also as test beds for AI processes and other emerging focus areas. So I'll conclude by formalizing all of this a bit, leaving you with the research lines of efforts that we're considering. The first two go hand in hand: formalized data sets and formalized state spaces. Exercises are instrumented for data collection generally, but work needs to be done to integrate that collection into a cohesive picture. This would involve labeling, cleaning, and publishing data sets to some exercise data repository that researchers have access to. But in order to label that data, to make it clean, work needs to be done to understand those state spaces. And we think that with a significant operator telemetry set, along with the objectives that they're trying to accomplish and the ground truth data laid on top of all that, perhaps we can codify the states involved with cyber tasks. I think it'd be pretty cool to get a tool that transforms a screen recording of people in an exercise and boil that down into a matrix of numbers that can be leveraged for teaching an AI process to do the same sorts of tasks and make the same sorts of decisions. That would all set the stage for some analysis of where best to apply AI for the operator, and where is it, you find out where it fits in that team. We'd like to discover the gaps as well as the priorities for developing those team processes with operators. And yeah, it would be great to know, say, what to tackle first and what would provide the most impact. And with an understanding of that state space, we can also grow a library of executable tasks that map to it. This can then be made available to autonomous agents to actually carry out the tasks that it determines are necessary. And while an actual autonomous operator would likely make a suggestion to its human counterpart, or at least ask permission before executing, it could be given a lot more latitude inside an isolated game space or a test bed, right? These ACOs, automated cyber operators, they need a place to grow from an infant to a toddler to elite. So with its concentration of machine learning experts combined with an experienced modeling, simulation, and exercise cadre, the SEI has a great foundation to explore the exciting future of this human-machine teaming in the cyber domain. The science is no longer fiction, and we're rolling up our sleeves to develop AI processes in cyber. We hope to continue gaining traction in realizing this sci-fi future, but only with its most positive connotations. Thanks for your time and attention, and I'd be happy to address any questions that you may have. Hi, everybody. We have a couple minutes for questions here, not a lot of time, but we wanted to have a quick discussion about this great topic. I have with me Dustin Updike. Dustin's an engineer on our team who's responsible for several of the tools we just got done talking about, specifically ghosts and several of the exercise assessments. So Dustin, why don't you just kick us off
with the with your thoughts on how the tooling has developed and how you've integrated that into these exercises.
Thanks, Jeff. I think one of the exciting things that we've noticed over the last couple of years is that the tooling around extracting valuable data out of a large amount of a data set or something like that has really matured. And that's exciting because a big part of the problem is we have all these different data sets. How do we extract quickly what might be the most interesting information for our customers to use?
Yeah, so it's no longer just a here's a packet capture. It used to be that was like the output of an exercise. Here's a network packet capture. That takes you a little bit, but doesn't get you very far in terms of the holistic, events and injects and the user activity, operator activity that can put together a cohesive picture. And so, are you optimistic with that tooling being able to extract better information about producing a normalized data set that actually could be fed into machine learning algorithms, at least for classification decisions? Or?
Yeah, I think one of the difficulties of machine learning projects in reality is the speed of which you can operate. And so, if you have a large amount of data, if it's disparate, if it's something you have to get from different sources, that takes time, right? And that sort of takes the edge off of what that information might mean for operators in the field. And so I think it's easy to forget that the tooling that allows you to get at that data and process it faster can really help that project. It's not part of the output that you hand over, right? It's not the information that you provide that operators can use. But it's an important part, an intrinsic part of getting at that data and doing something with it. There's been a lot of open source effort behind that that we can take advantage of and leverage. And so we've been looking at that, and we've been pretty excited about the leaps forward that people and organizations have been making in that front, for sure.
Yeah, it is exciting. I think it's a great pathway forward for us. Do you see any other questions come up in chat?
I have a question for you that we get asked all the time. How do you see the mixing of what we do in exercise versus what we do in real world ops in terms of data and how they can influence and touch upon one another? Have you given some thought to that?
Yeah, well, it is definitely a shame that oftentimes training gets put by the wayside. But we liken the cyber operator mission to, say, the pilots or other industries whereby, those jobs that people are always training, right? They're rarely actually doing the mission, but they're always training for the mission. So, these capabilities, I think, get us a lot further to provide that same kind of live, if you will, experience where you have training events going on as part of your normal work responsibilities, and maybe sometimes not even highlighted as training. Maybe it's just seamless. So those kind of activities, I think, will continue to reinforce this, especially when we're talking about integrating an automated partner in with a cyber operator, because as that entity gets more and more reliable and better at decision making, or at least presenting information for a decision to be made, then I think you're going to want to see that more and more being migrated from these test beds that we talked about into real world operations, again with that leash on there, so that we can kind of migrate this stuff out
migrate this stuff out slowly.
It's almost as if you use that testing and exercise outcome to influence in the best ways what you do in production tomorrow.
Yeah, exactly. So we're about out of time. So let me just wrap up with Dustin, your call on the science fiction part of this cyber operator augmented. Is it flying car difficulty, or is it teleportation difficulty? Are we going to be able to get to something in the next 5 years?
I think it's flying car in the sense that you still have an operator behind the wheel, right? And we can influence and provide information to the person actually making the calls and the driving.
Yeah, great. Thanks, everybody. If you want to, talk more about it, we'd love to engage in the conversation.
Hello, my name is Xinghan Lao, and I'm really excited to be able to share with you today a piece of work that my SEI colleagues and I have been working on for the past year on a project called AIDE, or Artificial Intelligence Defense Evaluation. Before I get started, just a quick thank you to our sponsor, which was the Department of Homeland Security, or more specifically, the Cybersecurity and Infrastructure Security Agency, or CISA. We really appreciate their generous funding of this work. Now let's start at the beginning. The genesis of the AIDE project came about because we noticed that a lot of organizations were turning to AI defenses to protect their networks. And we were interested in understanding both why they were doing so and what the ramifications were of them doing so. Now let's start with that why bit first. So there are two major advantages that organizations are hoping to gain by turning to AI defenses. First, to augment their analyst pool, and second, to counter the increasing speed of operation of cyber attacks. Let's start with augmenting the analyst pool. So there's a current shortfall of 500,000 cybersecurity staff positions in the United States alone. And organizations are looking for any way possible to maximize the staff that they do have. And one of the force multipliers they're hoping to leverage is AI. And they're hoping that AIs can do two things for them. First, to address some of the easier alerts, the more routine stuff, and thus free up their human analysts to handle harder problems, the more complex problems that might require really nuanced understanding of the network, the people using the network, and the business purpose of that network. Organizations are also hoping that AIs can catch threats that a human analyst would never be able to catch. That by virtue of an AI being able to ingest gigabytes or terabytes of data all at one time, they can find some really subtle or nuanced patterns that are indicative of some threat that a human analyst would just simply never be able to catch. The second advantage that organizations are hoping to gain is to counter the increasing speed of cyber attacks. So the bottom left here shows an article about the NotPetya attack in 2018. And this attack took down an entire Ukrainian bank's network in 45 seconds. Right? So by the time your system administrator or your operator or your analyst comes back from grabbing coffee or using the bathroom, it's already too late. The damage is already irreversible. To be able to counter an attack that's moving at that speed, you need to be able to move at near machine speeds. And AI is one of the tools that organizations are hoping to turn to gain that capability. So there are some advantages that our organizations are hoping to gain from AIs, but AIs can also go really wrong. So the top article here is about Cylance, which is a piece of endpoint malware detection software. And some researchers found last year that by appending a selected list of strings to a malicious file, which is another way of saying by taking some benign code snippets and appending them to the end of malware, they were able to fool Cylance to the point where they could completely avoid detection of the malware. And in fact, this was a highly successful method. It worked for 100% of the top 10 malware for May of 2019, and close to 90% of a larger sample of 384 pieces of malware. And it's not just researchers that are figuring out how to make our AIs go wrong. It's our adversaries as well. So the bottom article here is about a Russian espionage group called Fancy Bear. And what they're trying to do is that they're trying to strip down some initial infector piece of software that they have to gain a foothold on a network. They're trying to strip that down specifically to defeat machine learning-based defenses. And that brings me to the purpose of the AIDE project. So our assessment capabilities ultimately dictate how well we can test our own defenses. And it's now public knowledge that our adversaries are working to evade those AI defenses. Our assessors need that same information that our adversaries have in order to be able to accurately gauge our own defenses against our adversaries' capabilities. The nightmare scenario for us is that our assessors come up against one of these AI defenses, and they don't know how to get past. And so they give that organization a clean bill of health. They say, well, your security seems to be airtight. We can't get past. But our adversary would know how to get past that AI defense, and our adversary would be able to get onto our network. And we've now lulled ourselves into a false sense of security. Now, more formally, the problem that we're trying to solve in this project is to understand the capabilities of AI defenses in terms of how well they can detect malicious network activity, and to understand how those defensive capabilities can be bypassed. And the approach we're taking is to develop a testing methodology for AI defenses, both to identify their capabilities and the ways that they can be bypassed. Now, in this initial round of the A project, we worked on a proof of concept testing methodology, but this is something that we're hoping to eventually grow out into a comprehensive testing methodology. Now, what does this methodology look like? It can be broken down into 3 major categories of steps. So the first category is the setup steps. So we do things like creating a test network environment. We obtain some AI network defenses and put them and install them on that network. In this initial round of the project, we used commercial off-the-shelf defenses because that was what was easily available. We train those defenses on the normal network background traffic that we have when the network is operating normally. And then in yellow, we perform a baseline evaluation. So we have an attack that we execute against that network, and we see whether or not our AI-based network defense actually catches it. And then in blue, we try to bypass detection by that AI network defense. We're using things like obfuscation or data poisoning or both in order to avoid our attack from being detected when we execute it. Now let me talk about each of these steps in a little bit more detail. So let's start with the network. Well, rather, we're going to talk about an organization first, because networks tend not to exist in isolation. They exist because they need to serve some purpose for an organization. So what we did was we created a software development firm. And on the left here, you see the org chart for that firm. And the firm has 99 different employees across 5 different divisions and 3 levels of management. And each of these employees, and thus each user on the network, has their own unique behavior. They have customized work schedules. They come in and out of the office at different times of the day, and they go about their work tasks in a different manner. They have role-specific work tasks. So somebody who on the IT help desk might do things like using remote desktop to connect to somebody else's machine in order to do some IT maintenance task. Somebody who's working in accounting might access sensitive Excel spreadsheets that contain financial information about the organization. We've also assigned each of these users personal hobbies, so that govern their personal use of the corporate network. So if you're into gaming, you'll go to gaming-related websites. If you're into gardening, you'll go to gardening-related websites. In addition to having all of these unique behaviors, we also ensure that each of our users has privileges and accesses that make sense by their role. So you're not going to find some intern in sales having system administrator access to the entire network. That's going to be reserved for the system administrator because he or she actually needs those privileges to be able to do his or her job. Once we defined all these behaviors out, we used an SEI-created piece of software called Ghost in order to actually simulate this user behavior, and we're collecting the resulting traffic for use for training and testing our AIs. If Ghost sounds familiar to you, it's because you may have heard Jeff Mattson already talk about Ghost and how they used it for a different purpose. So what do our AIs actually look like? So the AIs that we evaluated are a combination of static and learned rules. So static rules are likely familiar to anybody who's worked in cybersecurity. An example is, well, if a host sends web traffic to outside of the company, then an alert should be generated. It's incumbent upon the system administrator to ensure whatever static rules exist make sense for the network and serve the organization, and they serve the purpose that they're designed to accomplish. What the AIs have that differs is that they also have learned rules. An example of a very, very simple learned rule is if a host sends out any traffic to a host that is not communicated with in the last 10 days, then an alert should be generated. What's being learned here is what hosts have been, what hosts and a host has communicated with in the last 10 days. This is a very, very simple example of learning. More common in the AIs that we evaluated are complex learned rules. So for example, if a host sends unusual traffic to a host that it has rarely communicated with, and that host is not considered safe, then an alert should be generated. What does it mean for traffic to be unusual? That's a machine learning model. What does it mean for one host to rarely communicate with another? That's a machine learning model. What does it mean for a host to be considered safe? That's yet another machine learning model. And so the AIs that we're looking at tend to combine both static rules with these more complicated learned rules. So we have these AIs. What did we do with them? So we started by training the AIs. And what we provided for training is 1 month worth of normal background network traffic. Now, this choice of a month is because this is what the vendors claimed was required to fully train those AIs. After the AIs are done training, we then took a snapshot of each of them, and we used that snapshot for all of our evaluations in this project. Now, it's worth noting that as we're conducting our testing, the same normal background traffic is going to continue in the background because our workers are continuing to work, even if there are malicious cyber attacks going on. Of course, we'll also have the additional traffic that's generated as part of that malicious cyber attack that constitutes the test. Speaking of that test, here's their baseline evaluation attack. So it's a relatively straightforward data exfiltration attack, and it begins with a step 0, or pre-attack reconnaissance. It then transitions into getting initial access on the network through spear phishing. We establish a foothold, and then we install our command and control tools. Those command and control tools are then used to do things like privilege escalation, credential access, or network discovery. And ultimately, we perform lateral movement to the machines that actually contain the sensitive data. We collect up that data, and we exfiltrate it out of the network. And the high-level finding that we had was that all of the AIs that we evaluated were capable of detecting this baseline attack. And this is significant because it means that for typical assessment activity that we conducted, the AIs would actually stop the assessors. And so it would have an actual impact on the assessment activities that we're performing. So having seen that the AIs are effective against this baseline attack, we were interested in understanding whether or not we could bypass detection. So the first thing we looked at was obfuscation. So the idea behind obfuscation is that you change something about the attack such that you still accomplish the goal, but you do it in a way that's different and hopefully avoids detection by the AI. So one of the things you can do is try to use different tools or techniques to accomplish the same goals while generating different or lesser amounts of traffic that hopefully the AI is less sensitive to. We can also do things like going low and slow, right? By rate limiting the rate of our attack, we can hope that the AI no longer thinks that this is suspicious activity. We also looked at things like trying to perform our attack steps using machines of users that already perform similar activities as part of their job duties. So if we need to muck about with some databases, we try to do that from the database administrator's machine because that's a lot less suspicious than if we did the same mucking about from the intern in accounting. Based on these obfuscations, we then defined and executed a modified attack path, and we wanted to see if the AI could still detect it. Now, the modified attack path was actually fairly straightforward. We just reconfigured some of our tools, but that reconfiguration was critical. That was the difference between the AI detecting our attack and not detecting our attack. As soon as we reconfigured our tool, we were still able to accomplish the goal of the attack path while completely bypassing detection by our AI. The second thing we looked at was data poisoning. So the idea behind data poisoning is that you create this poison data, and you create it by performing benign activities that generate traffic that's similar to the types of traffic that you're going to generate during the attack. This poison data then becomes part of the training data for the AI, and it causes it to mislearn, right? You want the AI to think that the attack traffic that it's going to see is just normal background traffic. Of course, we took care to ramp up our poisoning slowly. It does us no good if our poisoning itself is what gets caught by the AI. And our finding was that the data poisoning enabled the attack path to completely bypass the AI defense. It mislearned, in fact, and no longer was able to catch the attack that we were launching. So to summarize the findings that we had, we found that the AIs we examined were capable of detecting our baseline attack path, and thus would pose an impediment to some of the assessment activities that we would normally do. However, by doing data poisoning and by doing obfuscation, we were able to then evade detection and still get past the AIs and into the network. So that's what we've done. Where are we hoping to go in the future with AIDE? So there's quite a few directions we're hoping to go. First, we're always looking to increase the realism of our traffic and our system environment. So for example, we're hoping to get some video conferencing software like Zoom or Skype installed so that we can simulate that kind of traffic on the network. We're also hoping to use replay traffic, because while we took a lot of care to define out this organization and to generate the traffic based on that organization and the users in that organization, there's no substitute for using actual traffic. And there are some technical challenges associated with convincing the AI that replay traffic is actually live traffic and of injecting an actual attack into replay traffic, but those are obstacles that we think we can overcome. We're always looking to expand out the range of attacks we consider in our methodology. We looked at a single attack path in this current work, but we're hoping to get that up to hopefully dozens. We're also always looking to increase the number of AIs that we're actually evaluating to get a better sense of the landscape of these AIs. In this project, we looked at an evaluation at a single point in time. We had that snapshot that we evaluated against, but you'd like to be able to know that, to have some assurance that your AI is going to work a couple weeks down the road, or a couple months down the road, or a couple years down the road. And that requires an evaluation over the course of time. And we're looking also to try to extend some of the testing and evaluation methodology that we've developed here to other types of AI systems, not just AI network defenses, but maybe other types of systems in cybersecurity, like endpoint detection software, or perhaps outside of cybersecurity altogether. And I'll throw it out there that we are actively seeking collaboration opportunities. So if anything that you've heard here today seems of interest to you, or you're interested in applying some of these techniques to other types of AI systems, please reach out and let's see where we can engage. And finally, let me close by just thanking the team that worked on this project. This is not my work alone. We could not have accomplished this project without the help of Dr. Grant Deffenbaugh, Cheslia Cribbs, and Brandon Marzik, and our interns, Reggie Savoy and Alec Woods. And with that, I'd like to thank you very much for your time and attention, and I hope you enjoyed the other presentations.
My name is Matt Carr. I'm a team lead and cyber exercise developer in the Cyber Workforce Development Directorate at the Software Engineering Institute. Last year, we were asked by the Cybersecurity and Infrastructure Security Agency, or CISA for short, to plan, execute, and support the first ever President's Cup cybersecurity competition. In this presentation, I'll walk through the history of the competition and give a demonstration of the platforms used to deliver the event. Finally, I'll talk about the benefits of this competition to the Department of Defense. First, what is the purpose of the President's Cup? Established by Executive Order 13870, the competition is designed to reward the best and brightest talent in the federal executive workforce. To cast the net as wide as possible, the President's Cup employs a set of online qualification rounds available to anyone with a .gov or .mil email address. Internet access and a modern web browser are the only system requirements for competing in the President's Cup. Creating a common playing field is crucial to the mission of finding the best talent, regardless of his or her computing resources. Using the National Initiative for Cybersecurity Education, or NICE, framework as a blueprint for challenge development, competitors face a variety of challenges across different cyber work roles and job tasks. This helps make the competition more relevant for the federal workforce, focusing on challenge tasks that they might find in the course of their current cybersecurity job. And by highlighting the cybersecurity workforce at the federal level, the competition hopes to put a dent in the 500,000 cybersecurity job vacancies across public and private sectors in the United States. Addressing this shortfall is one of the ultimate goals of the competition and is part of a multi-pronged approach by CISA to address this talent gap in the federal government and beyond. Switching gears to last year's inaugural competition, the first year's President's Cup was a whirlwind effort. The SEI was given approval to execute the competition in late July 2019, and the executive order required winners to be selected by the end of the calendar year. In that time, SEI developed a novel web-based competition platform, authored 82 technical challenges, and designed a 3D escape room video game for the finals that concluded on December 14th with a YouTube live stream event. For this year's President's Cup, we made many improvements, including designing separate tracks for the individuals competition, implementing partial credit challenges, making 2019 challenge content available on a number of platforms, including GitHub and YouTube, and partnering with CMU's Entertainment Technology Center to design a new video game experience that will debut at the finals this year. And before we start the demo, I'd like to recognize the 67 contributors across the Software Engineering Institute and the greater Carnegie Mellon University community that have contributed towards President's Cup success over the past 2 years. From challenge development to platform development, to support, to broadcast media, it takes a team effort to make this complex endeavor a reality. And now, on with the demo.
The President's Cup 2020 is coming. Prove that you have what it takes by competing as a team, or individual, or both. Registration opens July 27th. The team competition kicks off August 10th and includes challenges across the entire cybersecurity spectrum. Starting August 24th, the solo competition is split into Track A and Track B. Participants can compete in one or both tracks. All qualifying rounds will be remote participation. For more information, visit CISA.gov/President's Cup. Come prove you are the best cybersecurity professional defending our nation.
That video provides a nice overview of the competition. This is the competition landing page, located at presidentscup.cisa.gov. You see there's a New for 2020 section, Media Assets, Competition Rules, and Frequently Asked Questions that our support staff use regularly. We actually host the source code for the page up on GitHub, so we can easily make changes alongside our sponsor. With that, this is our launching point for the rest of the demo. We're going to go through these buttons and show off the different areas of the competition. First, we'll open the Teams competition. But before we can access the Teams site, we'll need to log into the President's Cup identity server. This is an open source SEI application, also available on GitHub, and provides the authentication mechanism for cyber workforce development's modern web apps. After we're logged in, let's take a look at the Round 2 leaderboard. We'll zoom in on the current leading team, and I want to point out the addition of partial credit challenges this year. We added the ability to earn partial credit based on feedback from last year's President's Cup. You can see this team received full credit for over half the Round 2 challenges and earned partial credit on 3 more of them. Now, because I have observer status on the game board, I can take a look at how competitors are solving challenges in real time. This is valuable to get a sense of technique, as well as see how quickly challenges are solved. This competitor is using Wireshark to analyze a packet capture for a Teams round challenge. We believe detailed analysis of these solve videos are valuable from a research perspective. Now let's take a step back to the landing page again and look at each of the individual tracks this year. As the kickoff video mentioned, individuals Track A includes incident response, and Track B includes exploitation challenges. We thought that this would separate competitors based on their respective skill sets, but it turns out that over half of individuals who qualified for Round 2 in Track A also qualified for Track B. Now, as we make our way over to Track B, you may also notice there are a number of perfect scores atop the Track B leaderboard. We're increasing the difficulty in Round 2 to ensure we don't have a repeat of that. Now let's move to the 2020 practice board. This board allows anyone with a .gov or .mil email address to log in and complete practice challenges. And we encourage all competitors to do so. The challenge I'm highlighting was written to show off what we call infinity challenges. Challenges where the correct answer is generated at launch time. When the challenge launches, A script determines the correct answer and populates a virtual environment with the means to find that answer. Each challenge includes instructions to get started, along with a link to any virtual machines deployed for the challenge. This particular challenge launches 20 Docker containers, each running a web server. You'll see those containers come up when I type in the docker ps command. Now, each containerized web server responds with a 6-digit number. The simple goal of this challenge is to provide the sum of all of those container numbers. Jeff Matson, a developer on our team, loves these bash one-liners, and he created a slick one-liner to solve this challenge with a minimal amount of typing. We're going to use the copy-paste functionality within the console viewer to paste in that one-liner to solve the challenge. Now that we have the answer, we're going to use copy-paste again to get that answer out of the virtual machine and into the submission box. Bear in mind, I only have 3 attempts to answer this challenge, and that's done by design to limit guessing. After I submit the answer, it shows I received full credit. And now I'm going to rate the challenge as easy, but also excellent. And I can provide some free text feedback as well. That competitor feedback is available to moderators within the application. We also provide the same feedback to our government sponsor. And now that we've taken a look from the competitor's point of view, let's switch gears and see how the challenge is developed. Here's the interface that challenge developers use to author documentation, as well as provide correct answers for each challenge. As we scroll down, you see the documentation authored in Markdown format. And the right side provides a preview of what the competitor will see. At the bottom, we have the opportunity to create different variants of the challenge. In our case, we just have one variant because it's being generated dynamically. Here we define a script, and that script runs inside of a Docker container. As a result, we have a lot of flexibility when generating the solution to this challenge. This is the script that executes when the challenge deploys. It creates some random numbers using a seed value, and that seed gets passed into a virtual machine inside the challenge's namespace. To build the virtual machine templates, we use a separate web app called TopoMojo. Like the others, this app is open sourced on GitHub. Inside the virtual machine, I'm going to show off a few Ansible playbooks that populate the Kali Linux VM with the containers you saw earlier. This playbook generates the same random numbers from the seed in the previous script, and this next playbook creates a container serving out each random number. So that's a walkthrough of what's happening on the back end, the workflow that our challenge developers use when they create each challenge. From there, we'll head to the President's Cup archive site, which contains hosted versions of last year's challenges and allows competitors to solve them using only a web browser. I've deployed challenges using my iPad, and they work great. The site gives each user 4 hours to complete as many challenges as they want, and they can reset each board as many times as they want. Each round from the 2019 competition is represented on the respective board. One of the unique things about this environment is that all the virtual machines deploy to a VMware cluster running in an Amazon Web Services data center. While the web applications you've seen are already containerized and running in the cloud, our sponsor asked us to move hypervisor workloads in that same direction. This is a first step towards having President's Cup running completely in the cloud. Now let's head to GitHub, where we've published open source code for over half of the 2019 challenges. For any challenge that's eligible to be open sourced from a licensing perspective, we published the source code before the 2020 competition started. This includes solution guides for each challenge. This gave 2020 participants an opportunity to learn from last year's competition, whether or not they participated. And this will be the pattern going forward. Every challenge we can open source becomes a learning tool after the competition ends. Finally, the last stop on our tour is YouTube. With the help of our broadcast media team and challenge developers, we developed walkthrough videos for over half of last year's challenges. As you heard, each one has a catchy soundtrack and provides text prompts that accompany the screen capture video. Where it makes sense, we provided links to the corresponding GitHub page for challenges that have both source code and a video walkthrough. And with that, we're back to our starting point. This concludes my demonstration of the 2020 President's Cup. Thanks for your attention. Now, after watching the demo, you may be asking yourself, how does this apply to the Department of Defense? Well, the DoD contributes more participants to the President's Cup than any other top-level department or agency. But aside from that fact, there are other benefits to the department. As part of the SEI's continued support to the DoD, we understand their interest in the quantitative assessment of cyber operators and teams. Quantitative measures of success are valuable in deciding which teams should be declared mission-ready and which teams require more training to get there. The open-source platform hosting the President's Cup competition provides a unique take on large-scale assessment of these cyber teams. Through repeatable deployments of virtual machine environments that vary in scale and complexity, cyber teams can be presented with a mission and evaluated on the techniques employed to complete that mission. Further, these scenarios can be presented in rapid succession, evaluating teams on their relative efficiency in completing all the scenarios encountered. For the President's Cup, teams have 8 hours to complete as many challenges as possible. A similar time limit can be employed for DoD cyber teams to work through various mission readiness scenarios by having well-defined measures of success and accurately measuring goal completion inside each virtual environment. The time to complete each task and ultimately each scenario can be measured and compared between teams. And while time provides one dimension for measuring team performance, it's hardly the only measure or even the best one. How a scenario is completed provides a potentially richer data set for analysis. Using the platform's observation mode, each team's technique can be visually recorded and compared against other participating teams. And while comparing cyber techniques used to achieve a mission objective is more involved than comparing the time taken to achieve that same objective, artificial intelligence and machine learning models for a given scenario allow those comparisons to be performed at scale. In turn, this level of analysis can provide quantitative views into the decision-making and behavior of top-performing cyber teams. To conclude, in this presentation, we discussed the history of the President's Cup, provided a behind-the-scenes look at how the competition is built and executed, and offered potential research opportunities for the assessment of cyber teams at the Department of Defense. For more information about the President's Cup, you can contact me at info@sei.cmu.edu. Thanks for your time.
So, congratulations for making it through the end of day 2 of our 2020 SEI Research Review. Wow, what a fantastic day. All really focused around all of the different cyber work and the kinds of areas that we're working on there. I was glued to it all day. I hope that you managed to catch it as well and come into it. Just to sort of recap, what I want to do is step back for just a minute and say, You know, what struck me all the way through the day really came from Roman's very first comments during his setting the stage this morning, when he talked about the different areas of resilience that we're really focused within at the SEI and beyond and elsewhere. So I mean things like operational resilience, things like designed-in resilience, organizational resilience, infrastructure resilience. And you know, taking all those things together, we really have resilience engineering that's really been focused on all through the day with these different talks. Starting with Corey, you know, who really talked about how difficult it is to actually understand all the different vulnerability paths within code and how to actually get that reverse engineering done. And the approaches that we're doing based on the new data that we have that are making real progress in terms of moving that way. But it's a really hard problem to sort of quote a later talk. You know, was it flying car or was it teleportation? I'm leaning more toward the teleportation side when it sort of talks into that area. But that was the Corey thing. And then we get into Ed Schwartz, and you know, Ed talked more about the details in reverse engineering and some of the things that we would have to do for the missing variable names. And you know, the cool thing about that is if you had asked me a couple of years ago, could you reconstruct variable names from binaries where they're gone, I would have said, not a chance, not a chance. And we really are getting to where that's happening and where it's really working and sort of coming into place that way. And you know, the Q&As that started right after that, right after Ed Schwartz's presentation, I think really brought out just how much these kinds of problems resonate with you and with your work that you have out there. The questions that came in were really fantastic. I love to see them. I love the dialogue that went back and forth with those. We have 2 more days of research review coming up Thursday and Friday. I encourage you, please keep the questions coming. Keep them driving. Sometimes it's a little bit intimidating on this new platform that we're all on these virtual things to, you know, form your thoughts into a chat window instead of raising your hands and asking them in a live session. But you know, it's part of what makes this really valuable. It's part of what really brings it to life. And we saw that basically when we have, you know, Bob and Will and Lori and all working together on a series of interrelated projects, getting to how are we going to handle the explosion of alerts? How are we going to handle all of the different automated code repair? How far can we push it? Can we push automated code repair? How much can we deal with the explosion of alerts and use machine learning to help us understand what to do in that world? You know, and then that all comes together with Bill and the panel that we had on supply chain. Because if you think about it, it's not about coding a particular thing or looking at one particular development. It's the entire ecosystem. It's the hardware and software coevolution. It's all of the different elements that have to come together for these really, really complex systems that we're building. So the problems are not getting any easier. The problems are getting significantly harder from every aspect that we're looking at it. And that really took us to the sort of the closing presentations with Jeff and Xinghan and Matt close to the end of the day, where we really said, okay, not only is the problem what's happening on the computer and the code, but what does the human interaction with this code look like? How do we train our users to do it? How do we get insight into the way that we're going to be able to guide the AI versus AI of the future that's going to be part of our defense world? So what I really got out of today was this increasing in complexity, this increasing set of problems, not only that make some really fascinating research and some fascinating projects that are coming in, but ones that we always have to stay on top of and try to get that resilience really nailed down. So this is the end of day 2. Tomorrow is Veterans Day, so we are taking a day off. I hope you get to take a day off as well. Thanks to all of our veterans out there, to all of you watching, to all of you who are not watching. We owe our freedom to you, and we truly are grateful for the sacrifice that you have made in history. So no event tomorrow. We will be back on Thursday. We have a full event coming in on Thursday to talk more about the software evolution and about what's happening with regard to some of the new approaches in software design, in software execution, and basically AI/ML with CI/CD. And if those acronyms don't make sense, come and join us on Thursday. Learn more about what we're doing in the DevOps world and in this kind of space. At the end of Thursday, we're going to have another one of our poster sessions. And I strongly encourage you, come to the poster sessions. Those poster sessions really, we've created those to give you the opportunity not just to type into chat, not just to type into the questions that way, but to turn on your microphone, to turn on your camera, to interact one-on-one with the PIs that are there, and interact with the other people who are there interested too. So it's not just you and the researcher, it's you and all of the other people that stand around the poster. We're trying hard to recreate that experience of coming and standing around a poster and learning more and giving some feedback on how your problems are associated with that. So I really look forward to seeing you again on Thursday. We will also have this on Friday that will come through that way. No posters on Friday, but another full session that we have in there. Of course, the website has the full agenda. You can see everything that's going to be happening. If you need to be registered in order to come to the poster sessions, I encourage you, you can still register if you have not, and enjoy these sessions. I hope you enjoy them as much as I have, and we will really look forward to seeing you again on Thursday. Have a wonderful Veterans Day, everybody. Bye-bye.